On April 6, 2026, 4 human beings flew behind the moon and disappeared. For 40 minutes, no signal reached Earth. No voice, no telemetry. No heartbeat data on the monitors at the Johnson Space Center in Houston. No proof, of any kind, that they were still alive. The crew of Artemis 2, NASA astronauts Reed Wiseman, Victor Glover, and Christina Koch, along with Canadian Space Agency astronaut Jeremy Hansen, drifted through a silence that no human had experienced in more than half a century. They were 252,756 miles from the surface of the Earth, farther than any human being had ever traveled from this planet in the entire history of our species, farther than the Apollo 13 crew who held the previous record for 56 years, and below them, filling every window of their Orion spacecraft, a capsule they had named Integrity, was a landscape that no person had ever truly seen with their own eyes. Not like this, not from this trajectory, at this distance, at this angle, not with the sun behind them and the far side spread out like a map of ancient catastrophe. What they saw was not what anyone expected, not the scientists, not the mission planners, not the astronauts themselves, despite years of training, field trips to analog sites in Iceland and Labrador, and months of studying orbital photographs taken by robotic probes. The far side of the moon is not simply the back of a familiar world, it is an alien terrain, where the near side, the face we see every night from our backyards, the face we have sketched and painted and photographed and sung about for millennia, is marked by vast, smooth plains of ancient lava, dark and flat and strangely peaceful. The far side is a fortress of craters. Billions of years of bombardment have scarred it beyond recognition. The crust there is thicker. The chemical composition is different. The geological story it tells contradicts almost everything we once believed about how our moon was formed, how it evolved, and why it looks the way it does. And when the Artemis 2 crew swept across this hidden hemisphere at nearly 61,000 miles per hour relative to Earth, they reported something that sent tremors through the science evaluation room at Mission Control. They saw flashes, brief, silent explosions of light on the darkened surface below, meteoroids slamming into the lunar regolith in real time, impacts so fast and so violent that no camera aboard the spacecraft could capture them. Only the human eye was quick enough. Only the human brain, evolved over millions of years to detect sudden motion against a still background, could process what was happening at the speed it was happening. 6 flashes, 6 impacts, 6 tiny explosions on the surface of a world with no atmosphere, no magnetic shield, no defense of any kind against the debris that streams through interplanetary space. Each flash lasted less than a second. Each marked the end of a meteoroid's journey through the solar system. A journey that may have begun millions or billions of years ago, when a collision between asteroids in the main belt beyond Mars liberated a fragment that slowly drifted inward toward the inner planets, perturbed by the gravitational pulls of Jupiter and Saturn, nudged by the faint pressure of sunlight, until it found itself on a trajectory that intersected the moon. Scientists in Houston erupted. There were, by one account, audible screams of delight from the lunar science team. But delight was not the only emotion in that room, because what those flashes revealed, what the entire far side reveals, if you understand the science, is something far more unsettling than a few rocks hitting the moon. It is a reminder that the moon is not a quiet companion drifting peacefully beside us through the calm of space. It is a battered shield, a record keeper, a witness to 4.5 billion years of cosmic violence, and behind it, in every direction, stretching to the edge of the observable universe, space is still shooting. The bombardment that scarred the far side has never stopped. It has only slowed. By the end of tonight, you're going to understand what the Artemis 2 crew actually witnessed on the far side of the moon, why the hidden hemisphere looks so radically different from the one we see, what lies buried beneath the largest crater in the entire solar system, why everything we thought we knew about the moon's formation is being rewritten right now by a handful of volcanic rocks pulled from the dark side's ancient soil, and what all of this means for our understanding of Earth itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. The moon has always been there, hanging in our sky, constant, familiar, close enough to see with the naked eye, yet far enough that no human visited it for 53 years. We have written poems about it, navigated oceans by it, and marked our calendars with its phases for thousands of years. We thought we knew it. We named its features. We mapped its craters. We collected its rocks and brought them home in sealed containers. We assumed the story was mostly told. We assumed the face we could see was representative of the whole, that the half we knew told us enough about the half we could not observe. We were wrong. The moon has been hiding something, and in April of 2026, 4 people went to look at it. Now let's begin. To understand what the Artemis 2 crew saw, and why it matters so deeply, we first need to understand what the moon actually is, how it relates to Earth, and how remarkably little of it humanity has ever truly examined. The moon orbits Earth at an average distance of roughly 238,900 miles. In the language of astronomy, that is about 1.28 light seconds, meaning a beam of light. Travelling at 186,282 miles per second, the fastest speed permitted by the laws of physics, takes just over 1 second to cross the gap between our world and the moon. When you look up at the moon on a clear night, you are seeing it as it was approximately 1.3 seconds in the past. In cosmic terms, this is practically nothing. The moon is our neighbour. It is close enough that we can see its surface features with the naked eye. Close enough that a modest backyard telescope reveals individual craters and mountain ranges. Close enough that, with sufficient energy and engineering, we can send human beings there and bring them back. But the closeness is deceptive. 239,000 miles is an abstraction. To make it tangible, consider that if you could drive to the moon at highway speed, say 70 miles per hour, with no stops for fuel, food, or sleep, the journey would take approximately 142 days, nearly 5 months of non-stop driving, 24 hours a day, just to reach the nearest celestial body. The distance is roughly equivalent to driving around the Earth's equator 9.5 times. Every astronaut who has travelled to the moon has crossed a gulf that dwarfs anything in ordinary human experience. A gap between 2 worlds that looks small on a diagram but feels, to those who traverse it, like the edge of everything. Getting there requires extraordinary violence. The Space Launch System rocket that carried the Artemis 2 crew to the moon produced 8.8 million pounds of thrust at liftoff, more thrust than any operational rocket in the world. That is enough force to accelerate a fully loaded Boeing 747 to takeoff speed in less than a second. The rocket consumed hundreds of thousands of gallons of cryogenic propellant, ultra-cold liquid hydrogen and liquid oxygen, stored at temperatures far below freezing and ignited in a controlled inferno that generated temperatures exceeding 5,000 degrees Fahrenheit in the combustion chambers. All of this fury, all of this energy, all of this noise that rattled windows for miles around the Kennedy Space Center was necessary to do one thing: escape the gravitational grip of Earth and send 4 people on a trajectory toward a body 239,000 miles away. The journey took approximately 4 days. 4 days of coasting through the vacuum between 2 worlds, watching Earth shrink behind them in one window while the moon grew in another. For the first time since December of 1972, human beings watched this slow transformation happen. The gradual swapping of worlds, the quiet realization that they were leaving the only home our species has ever known, and approaching a world that is familiar in appearance, but alien in every other respect. The moon itself is roughly 2,159 miles in diameter. That is about 27% of Earth's diameter, or roughly 1/4 its size. To put this in perspective, the continental United States, from the Atlantic coast to the Pacific, spans roughly 2,800 miles. The moon is smaller than that. You could fit the moon's diameter inside the width of North America with room to spare. In volume, the moon could fit inside Earth roughly 49 times. In mass, the relationship is even more dramatic. Earth is 81 times more massive than the moon. The moon's gravity at its surface is about 1/6 of Earth's, strong enough to hold a person and a spacecraft, but weak enough that an astronaut in a spacesuit can jump nearly 6 times higher than they could on Earth. To visualize the Earth-Moon system at a scale you can hold in your mind, imagine Earth as a basketball, roughly 9.5 inches in diameter. At this scale, the Moon would be a tennis ball, about 2.5 inches across. The distance between them would be approximately 23.5 feet, the length of a large living room. Picture that in your mind. A basketball sitting in one corner of a room, a tennis ball hovering in the opposite corner. The basketball is spinning. The tennis ball is orbiting it slowly, always keeping the same face turned toward the larger ball. Everything that has ever happened in the history of human spaceflight, every orbit, every spacewalk, every space station, every lunar mission, has occurred within the space between that basketball and that tennis ball. That is our domain. That is the extent of human experience in the cosmos. And all of our lunar exploration, 12 moonwalkers, 6 landing sites, 842 pounds of samples returned, occurred on one face of that tennis ball, the face pointing toward the basketball. The opposite face remained untouched, unseen by human eyes at close range until Artemis 2. The reason for this is tidal locking, and it is worth understanding in some detail because it shapes everything about the Moon's relationship with Earth. Tidal locking is a consequence of gravitational interaction between two orbiting bodies. It is not unique to the Earth-Moon system. Many moons in the solar system are tidally locked to their parent planets, including the 4 largest moons of Jupiter, discovered by Galileo in 1610. Tidal locking occurs because the gravitational pull of a larger body on a smaller one is not perfectly uniform. The side of the smaller body facing the larger body experiences slightly stronger gravity than the far side because it is slightly closer. This differential creates tidal bulges, subtle elongations in the shape of the smaller body, stretching it very slightly along the line connecting the two centers of mass. If the smaller body is rotating faster than it is orbiting, which is almost always the case initially, these tidal bulges do not stay perfectly aligned with the larger body. They are carried ahead of the line between the two centers by the rotation, like a wave that cannot quite keep up with the shore. The gravitational pull of the larger body on these displaced bulges creates a torque, a rotational drag, that slowly, over millions or hundreds of millions of years, reduces the smaller body's rotation rate. Eventually, the rotation slows until it exactly matches the orbital period. At that point, the tidal bulges remain permanently aligned, no torque is generated, and the configuration is stable. One face permanently points toward the larger body. The opposite face permanently points away. For the Moon, this process was completed long ago, probably within a few 100 million years of its formation, when tidal forces were much stronger because the Moon was much closer to Earth. Today, the Moon takes approximately 27.3 days to complete one orbit around Earth, and exactly the same duration to complete one rotation on its axis. The synchronization is precise. The same hemisphere has faced Earth for billions of years. This is why we always see the same face of the Moon, and it is why the other face, the far side, remained a complete mystery until the space age. The far side is not dark. Let us be very clear about this, because the misconception is so deeply embedded in popular culture that it distorts public understanding. The phrase "dark side of the Moon," popularized by a famous album, by science fiction films, by countless casual references, implies that the far side is shrouded in perpetual shadow. It is not. The far side receives exactly as much sunlight as the near side over the course of a full lunar cycle. Every point on the lunar surface experiences roughly 14 Earth days of continuous sunlight, followed by roughly 14 Earth days of continuous darkness. A single lunar day, from sunrise to sunrise at any given point, lasts about 29.5 Earth days. The cycle is slow but perfectly regular, and it applies equally to both hemispheres. The far side is not dark in any physical sense. It is dark only in the sense of being unknown, hidden from our view, inaccessible to Earth-based telescopes, a blank space on the map of human knowledge. The consequences of this one-sided visibility run deep. For all of human history prior to the space age, our understanding of the Moon was derived entirely from one hemisphere, the near side. astronomers mapped its features with increasing precision from the time of Galileo onward, assigning names to its craters, its mountains, its maria. By the mid-20th century, the near side was one of the most thoroughly mapped surfaces in the solar system. Cartographic projects had identified and catalogued thousands of features. Photographic atlases showed the near side in exquisite detail at every phase of illumination. Scientists built geological models of the Moon based entirely on near-side evidence, models that assumed, implicitly, that what they were seeing was representative of the whole. The far side was, by definition, invisible to all of this work. Radio telescopes could not image it. Optical telescopes could not observe it. The only way to see the far side was to send something behind the Moon to look at it. And until the late 1950s, no one had the capability to do this. That blank space began to fill on October 7, 1959, when the Soviet probe Luna 3 swung behind the Moon and captured the first photographs of the far side. The images were crude, grainy, low resolution, transmitted across 239,000 miles of space, using radio technology that was primitive by modern standards. But even through the noise, one thing was immediately and startlingly clear. The far side looked nothing like the near side. The shock was profound. Scientists had spent decades studying the near side through telescopes, mapping its features in exquisite detail, naming its craters after great thinkers and explorers, categorizing its geology, building models of its formation. They had assumed, reasonably, they thought, that the far side would be broadly similar, a different arrangement of features perhaps, but the same general mix of dark maria and bright highlands that characterized the visible face. Luna 3's photographs shattered that assumption in an afternoon. The far side was overwhelmingly bright, overwhelmingly cratered, overwhelmingly ancient, and overwhelmingly empty of the dark volcanic plains that defined the near side's appearance. Where the near side is approximately 31% maria, the vast, dark, smooth plains of solidified basaltic lava that form the recognizable patterns of the man in the moon or the rabbit in the moon. Depending on your cultural tradition, the far side had almost none. Less than 1% of the far side surface is covered by maria. Instead, it is an overwhelming chaotic landscape of overlapping impact craters, layer upon layer of them, accumulated over 4 billion years of bombardment, with virtually no volcanic resurfacing to erase or soften the scars. Subsequent missions. The American Lunar Orbiter probes in the mid-1960s, the Clementine spacecraft in 1994, the Lunar Prospector in 1998, Japan's Kaguya Orbiter in 2007, India's Chandrayaan-1 in 2008, and NASA's Lunar Reconnaissance Orbiter, which has been mapping the Moon in extraordinary detail since 2009, built progressively sharper and more complete pictures of the far side. The Lunar Reconnaissance Orbiter alone has captured more than 1 million images of the lunar surface at resolutions as fine as 1.5 feet per pixel, revealing features as small as individual boulders. These images confirmed and deepened the impression left by Luna 3. The far side is a fundamentally different world from the near side, not just visually, structurally, chemically, geologically. In almost every measurable parameter, the two hemispheres diverge. The far side highlands are pale. They are ancient, among the oldest surfaces in the solar system that you can touch. They are composed primarily of a mineral called anorthosite, a type of rock made up almost entirely of plagioclase feldspar, a light-colored mineral that floated to the top of the Moon's global magma ocean when the Moon first formed. These highlands are the Moon's original crust, or very close to it, the first solid surface that formed as the molten Moon cooled and crystallized 4.5 billion years ago. The age of this surface deserves emphasis. 4.5 billion years is a number that passes through the mind without leaving a mark, unless you force yourself to engage with what it means. Consider, the oldest known rocks on Earth's surface are approximately 4 billion years old, found in the Acasta Gneiss Complex in Canada's Northwest Territories. They are geological celebrities, precious fragments of the earliest Earth, studied intensively because they are so rare. Virtually everything older has been recycled by Earth's geological engine. The far side of the Moon preserves surfaces that predate the Acastoness by 500 million years. 500 million years. That is longer than the entire history of complex animal life on Earth. Longer than the interval from the Cambrian explosion to the present day. The far side's surface was already ancient when Earth's oldest surviving rocks were forming. It was already ancient when the first continents were being assembled. It was already ancient when Earth's atmosphere first accumulated significant oxygen, when the first single-celled organisms appeared, when life itself began. Think of it this way: if the near side of the Moon is a painting, a composed, layered, visually coherent image with dark plains and light highlands, arranged in a pattern that almost looks intentional, then the far side is the raw canvas before the painter arrived. Untouched, unsmoothed, every mark visible, every imperfection preserved, every collision recorded in stone for eternity. This asymmetry between the two hemispheres has been one of the central mysteries of planetary science since the space age began. Why does the Moon have two faces? Why is the crust thicker on one side? Why did volcanic activity concentrate on the near side and largely bypass the far side? These are not idle questions. They are questions about the fundamental nature of the Moon itself. They are questions about the origin and evolution of the Earth-Moon system. And they are questions that, despite 6 decades of study, remain incompletely answered. To appreciate the scale of the far side's most dramatic feature, consider the South Pole Aitken Basin, which the Artemis II crew flew directly over during their 7-hour flyby. This is the single largest recognized impact structure in the entire solar system, not just on the Moon, but anywhere we have been able to observe with sufficient resolution to identify impact craters. It dominates the southern portion of the far side, stretching roughly 2,500 kilometers, about 1,550 miles, across in its longest dimension. If you superimposed it on a map of the United States, it would stretch from Chicago to Houston. It plunges more than 8 miles deep in places, making it the deepest crater on the Moon and one of the deepest impact structures known anywhere. The name itself tells part of the story. The basin is named for the two features that mark its approximate extent: the lunar South Pole at one end and the crater Aitken at the other. But the name understates the scale. The South Pole Aitken Basin is not a crater in any ordinary sense of the word. It is a scar, a geological wound so vast that it altered the Moon's shape, thinned the crust by miles, exposed mantle material at the surface, and may have redistributed the Moon's internal chemistry in ways that determined the next 4 billion years of geological evolution. It is the most consequential impact event in the Moon's history after the Moon-forming impact itself. If you were standing at the center of this basin, you would have no idea you were inside a crater. The rim would be far beyond the horizon in every direction. The floor would simply look like terrain, rough, cratered, ancient terrain, with no visible boundary to indicate that you were at the bottom of a wound created by one of the most violent events in the history of the inner solar system. That event occurred roughly 4.25 billion years ago. The energy it released has been estimated at more than 1 trillion times the energy of the atomic bomb dropped on Hiroshima. 1 trillion. To make that number tangible, consider that 1 million seconds is about 11.5 days. 1 billion seconds is about 31.5 years. 1 trillion seconds is about 31,700 years. The difference between these scales, day, decade, epoch, is the difference between a large explosion and the force that created the South Pole Aitken Basin. It is a force that is almost impossible to comprehend. It cracked the Moon's crust, excavated miles of rock, melted vast volumes of the underlying mantle, and may have deposited the remains of the impacting body deep in the lunar interior, where they remain to this day. The impactor itself was likely tens of miles across, perhaps 100 miles in diameter or more, based on scaling relationships between impactor size and crater diameter, at the velocities typical of asteroid impacts in the inner solar system, roughly 25,000 to 45,000 miles per hour. The kinetic energy of a body this size striking the Moon would have been sufficient to excavate the observed basin, eject material hundreds of miles from the impact site, and generate seismic waves strong enough to fracture the crust on the opposite side of the moon. Some models suggest that the impact may have temporarily reshaped the moon itself, distorting its figure from a sphere into something slightly oblate before gravitational equilibrium was restored. And buried beneath this basin, detected by gravity mapping spacecraft in the 21st century, sits a mass anomaly so large and so dense that its discoverers compared it to a block of metal 5 times the size of the big island of Hawaii. This mass extends more than 300 miles below the surface. It weighs at least 2.18 quintillion kilograms, and it has been sitting there, warping the moon's internal gravity field, since before life existed on Earth. This is what the Artemis II crew flew over during their flyby. This is what lies beneath the terrain they photographed. They could not see it, they could not feel it, but it was there, an enormous, ancient, metallic remnant of the collision that may have shaped the moon's destiny forever. The Artemis II mission was not designed for a landing. It was a test flight, the first crewed flight of both the Space Launch System rocket and the Orion spacecraft. The primary goal was to validate the systems that will support future missions to the lunar surface. The crew launched on April 1st, 2026, from Launch Pad 39B at the Kennedy Space Center, propelled by 8.8 million pounds of thrust, watched by nearly 350,000 spectators on the space coast of Florida. They spent 10 days in space, traveled 695,081 miles, tested life support and navigation systems, performed manual piloting demonstrations, and gathered data on radiation exposure, exercise physiology, and emergency procedures. The crew of 4 represented a cross-section of the most experienced test pilot and scientist astronaut talent available to the Artemis program. Commander Reed Wiseman, a Navy test pilot and veteran of a previous expedition to the International Space Station, led the mission. Pilot Victor Glover, also a Navy test pilot and an experienced ISS crew member, served as the spacecraft's pilot and became the first black astronaut to travel beyond low Earth orbit. Mission specialist Christina Koch, a physicist and engineer who previously set the record for the longest continuous spaceflight by a woman during a 328-day stay on the International Space Station, managed the science operations and documentation. And mission specialist Jeremy Hansen, a Canadian Forces fighter pilot and the first non-American astronaut to fly on a lunar mission, operated the telephoto camera systems that produced some of the flyby's most detailed images. Together, they represented 2 space agencies, 4 decades of combined flight experience, and the collective expertise needed to operate a spacecraft in deep space, while simultaneously conducting the most ambitious observational program of the lunar far side ever attempted by a crewed mission. But the moment that will define this mission, the moment that will be remembered when the engineering data has long since been archived, was Day 6, April 6th. The flyby, 7 hours of human observation over the far side, with more than 7,000 photographs taken, 6 meteoroid impact flashes witnessed, a total solar eclipse experienced from behind the moon, and the first human observation of Earthset since the Apollo era, the moment when Earth sank below the lunar horizon and vanished from view. Then came the silence, 40 minutes of communication blackout, with the moon itself blocking every radio frequency between the Orion spacecraft and the deep space network on Earth. 4 human beings, entirely alone, with the far side rolling beneath them and the stars burning overhead in a clarity that no one on Earth will ever experience. Something is wrong with our assumptions about the moon. The far side has been telling us this for 67 years, since the first lunar photographs revealed a world we did not expect, and yet the message has been slow to penetrate public consciousness. The moon remains, for most people, a familiar light in the sky, a companion, a decoration, a metaphor, the idea that it harbours a profound geological mystery, a mystery that connects to the origin of life on Earth, to the radiation environment beyond our planet's protection, to the mechanics of planetary formation throughout the galaxy, remains largely unknown outside the scientific community. The Artemis II crew brought human eyes to that world for the first time in half a century. What they saw, and what the science of the past 5 years has revealed, compels us to reconsider everything. The moon should not exist the way it does. That sentence sounds like an overstatement. It is not. It reflects a genuine, persistent frustration in the planetary science community, a recognition that our closest celestial neighbor defies easy explanation in ways that continue to surprise and confound researchers decades after the first lunar samples were returned to Earth. The moon is anomalous in nearly every measurable way. It is too large, too light, too similar to Earth, and too different from everything else. Begin with size. The moon is roughly 1/4 the diameter of Earth. That ratio, 1:4, is the largest moon-to-planet size ratio of any rocky planet in the solar system. Mercury and Venus have no moons at all. Mars has 2 tiny captured asteroids, Phobos and Deimos, each only a few miles across, insignificant specks compared to their parent planet. Only Earth has a companion large enough to be a significant gravitational partner. The moon is not a minor satellite. It is a world in its own right, large enough to be spherical, large enough to have its own geological history, large enough to exert measurable gravitational effects on Earth, including the tides that have shaped coastlines, ecosystems, and even the evolution of life for billions of years. Now consider density. Earth's average density is roughly 5.5 grams per cubic centimeter, reflecting its large iron-nickel core, which makes up about 32% of the planet's total mass. The moon's average density is only about 3.3 grams per cubic centimeter. Its iron core is small, estimated at only 300 to 400 miles in radius, compared to Earth's core radius of roughly 2,165 miles. In proportional terms, the moon's core is a much smaller fraction of its total volume than Earth's. Something drained the moon of iron, or prevented it from accumulating iron in the first place. The explanation for this deficit is one of the keys to understanding lunar origin. Then there is composition. The Apollo missions returned 842 pounds of lunar rock and soil between 1969 and 1972. Those 6 missions, Apollo 11, 12, 14, 15, 16, and 17, collected samples from a narrow band of the near side between roughly 9 degrees south and 26 degrees north latitude, spanning a longitudinal range of less than 40 degrees. In total, the 12 moonwalkers sampled an area that would fit comfortably inside the state of Wyoming. It was a breathtaking achievement, the most ambitious scientific fieldwork in human history. But it was also geographically limited. Everything we learned from Apollo about the moon's composition, age, internal structure, and volcanic history was extrapolated from samples collected at 6 points on one hemisphere of one world. The other hemisphere, the far side, remained unsampled until 2024. Analysis of the Apollo samples revealed 2 remarkable findings. First, the oxygen isotope ratios in lunar samples are nearly identical to those in Earth's mantle rocks. Oxygen is the most abundant element in the Earth's crust and mantle, and it comes in 3 stable isotopes: oxygen-16, oxygen-17, and oxygen-18. The ratios between these isotopes vary slightly from one solar system body to another, providing a kind of chemical fingerprint. The fact that the moon's oxygen isotope fingerprint matches Earth's almost exactly suggests a shared origin, that the moon was made, at least in part, from the same material as Earth. Second, the lunar samples showed that the moon is profoundly depleted in volatile elements. Volatiles are substances that evaporate or vaporize at relatively low temperatures, elements like water, sodium, zinc, potassium, and lead. Compared to Earth, the moon has far less of these materials. The depletion is dramatic. The moon contains roughly 100 to 1,000 times less water than Earth's mantle, and is similarly depleted in other volatile species. This depletion implies that the moon's constituent material was subjected to extreme heat at some point during its formation. Heat so intense that it drove away anything that could be vaporized, leaving behind only the most refractory, high-temperature materials. The volatile depletion is not consistent with a cold formation process. It demands temperatures of thousands of degrees, temperatures that could only be produced by an event of extraordinary violence. These 2 clues, the compositional match with Earth and the depletion of volatiles, pointed toward a formation mechanism involving both shared material and extreme temperatures. No gentle process could produce both features simultaneously. The moon's origin required violence, an event energetic enough to vaporize rock and mix the material of two bodies into one. But the classical theories of lunar origin could not accommodate both clues simultaneously. The fission hypothesis, first proposed by George Darwin in 1879, suggested that the moon spun off from a rapidly rotating early Earth, like a droplet flung from a spinning top. This would explain the compositional match. The moon would literally be made of Earth material, but it required Earth to have been spinning so fast that its day lasted only about 2.5 hours. No known mechanism could produce such extreme rotation without also disrupting the proto-Earth beyond recovery. And no process could account for how the system subsequently lost enough angular momentum to reach its current state, with Earth rotating once every 24 hours and the moon orbiting once every 27 days. The capture hypothesis proposed that the moon formed elsewhere in the solar system and was later captured by Earth's gravity. This could explain compositional differences, but not the compositional similarities. And gravitational capture without a collision is extraordinarily difficult. For the moon to have been captured intact, it would have needed to approach Earth at precisely the right speed and angle, slow enough to be trapped by gravity, but not so fast as to fly past or crash. The probability of this occurring naturally, without a third body to absorb the excess kinetic energy, is vanishingly small. Even if capture occurred, the resulting orbit would have been highly elliptical, not the nearly circular orbit we observe. Circularizing a captured orbit through tidal dissipation would have taken an extremely long time and should have left detectable signatures in the orbital parameters that are not present. The capture hypothesis has been effectively ruled out for the Earth-Moon system, though capture may explain the origin of some small, irregular moons in the outer solar system. The co-accretion hypothesis proposed that Earth and Moon formed together from the same region of the protoplanetary disk. This was the most intuitive model, and it could explain the compositional similarities naturally. But it could not explain the Moon's small iron core. If Earth and Moon formed from the same material at the same location, they should have similar proportions of iron and silicate. Earth is about 32% iron by mass. The Moon is only about 10%. Something removed iron from the Moon's formation process, and co-accretion could not explain what. The model also struggled to explain the Moon's angular momentum. The specific orbital energy of the Earth-Moon system is difficult to reproduce from a co-accretion scenario without invoking special conditions that undermined the model's simplicity. By the mid-1970s, all three classical theories had been largely abandoned. The Apollo data was too constraining, too specific, too full of contradictions for any simple model to survive. The lunar samples had placed the Moon in a narrow compositional corridor, similar enough to Earth to require a shared origin, depleted enough in volatiles to require extreme heating, and iron poor enough to require a selective process that separated metal from silicate. No single classical model could navigate all three constraints simultaneously, and then came the breakthrough. In 1975, two independent research groups proposed what is now called the giant impact hypothesis. William Hartmann and Donald Davis, working at the Planetary Science Institute in Tucson, Arizona, published a paper suggesting that the Moon formed from debris ejected by the collision of a large body with the proto-Earth. Independently, Alastair Cameron and William Ward at Harvard reached a similar conclusion using different modeling approaches. The theory they collectively proposed goes like this. Roughly 4.5 billion years ago, when the solar system was still assembling itself from a vast disk of gas and dust orbiting the young sun, a body approximately the size of Mars, roughly 4,200 miles in diameter, about half the size of Earth, collided with the proto-Earth. This body has been named Theia, after the Titaness of Greek mythology, who was the mother of Selene, goddess of the moon. The collision was not head-on. It was a glancing blow, striking the proto-Earth at an oblique angle at a speed estimated at roughly 25,000 miles per hour. The name Theia carries a weight of meaning that the scientists who coined it may not have fully intended. In Greek mythology, Theia was the goddess of sight, the deity who endowed gold and silver and precious stones with their radiance. It is fitting, in a grim way, that the body which destroyed itself to create the moon was named after a goddess of vision. The moon, after all, is the most visible object in our night sky, a testament to an act of destruction so vast that its product has illuminated human nights for as long as there have been human eyes to see it. The result was an event of almost inconceivable violence. The impact liquefied most of Earth's surface, vaporized vast quantities of rock, and shattered Theia into fragments. The dense iron cores of both bodies, being the heaviest material, sank inward under gravity and merged, forming the large iron-nickel core that Earth possesses today. This is why the moon has so little iron. Most of Theia's iron ended up in Earth's core rather than in the orbiting debris. The lighter silicate material, the mantles and crusts of both proto-Earth and Theia, was ejected outward into orbit, forming a superheated disk of vaporized and molten rock that encircled the newly reconstituted Earth. This debris disk, glowing with the heat of formation, gradually cooled, clumped together under its own gravity, and within perhaps a century, a geological instant, coalesced into the moon. The physics of this event deserve a moment of sustained attention, because they illustrate just how different the early solar system was from the orderly, predictable place we inhabit today. When Theia struck the proto-Earth, the collision energy was so enormous that both bodies were partially or entirely melted. The impact site, if you can even call it a site, given that the entire surface of the planet was affected, experienced temperatures exceeding 10,000 degrees Fahrenheit. Rock does not merely melt at these temperatures, it vaporizes. The impact produced a cloud of superheated rock vapor, a silicate atmosphere, essentially, that enveloped the reconstituted Earth and extended outward into orbit. This cloud was opaque, incandescent, and lethally hot. If you could have observed the Earth from space in the hours after the Theia impact, you would have seen not a planet but a glowing ball of magma surrounded by a swirling disk of vaporized rock, the whole system radiating heat at temperatures that would dwarf the surface of the Sun's photosphere. The debris disk that formed from this material was not a calm, orderly structure. It was turbulent, chaotic, riddled with density variations and thermal gradients. Clumps of molten material collided with each other, merged, broke apart, re-merged. The disk extended outward to several Earth radii, perhaps as far as 5 or 6 times Earth's current radius, and its inner edge was so close to Earth that material was constantly falling back to the surface, while new material was being added to the disk by outward flowing vapor. The process was simultaneously constructive and destructive, building the moon from the outside while stripping material from the inside. Within this violent environment, the moon began to coalesce. Computer simulations by Robin Canup, Eric Asfaug, and others have shown that the assembly process was remarkably fast by geological standards. Within a few orbital periods, perhaps a few days to a few weeks, the largest clumps in the disk had gravitationally attracted enough material to become self-gravitating bodies. Within a century, possibly much less, the disk had consolidated into a single large body, the moon. It was born hot. Its entire surface was molten. A global ocean of magma stretching from pole to pole, hundreds of miles deep, glowing with the residual heat of its violent formation. This magma ocean is critical to understanding everything that followed. As the molten moon cooled, a process that took perhaps a few tens of millions of years, minerals crystallized out of the magma in a specific sequence dictated by their melting points and densities. The first minerals to crystallize were dense, iron and magnesium-rich silicates, olivine and pyroxene, that sank downward through the magma toward what would become the mantle. As crystallization proceeded, lighter minerals began to form. The most important of these was plagioclase feldspar, a calcium and aluminum-rich silicate that was less dense than the surrounding magma. Instead of sinking, the plagioclase floated. It accumulated at the surface of the magma ocean like scum on a pond, gradually building up into a solid crust of anorthosenic rock, the pale, ancient highland material that dominates the far side today. The last dregs of the magma ocean, the residual liquid that remained after most of the crystallization was complete, were enriched in all the elements that did not fit comfortably into the crystal. Structures of olivine, pyroxene, or plagioclase, These incompatible elements included potassium, the rare earth elements, phosphorus, thorium, and uranium, the suite of materials scientists call creep. This residual liquid was sandwiched between the newly formed crust above and the crystallized mantle below, forming a creep-rich layer that would later play a decisive role in the Moon's geological evolution. If the magma ocean had cooled uniformly, if every part of the Moon's surface had solidified at the same rate, under the same conditions, then the resulting crust should have been approximately the same thickness everywhere. The creep layer should have been distributed roughly evenly. The Moon should have been symmetrical. It should have had one face, not two. The giant impact hypothesis is elegant because it resolves in one stroke almost all the problems that plagued the earlier theories. The compositional similarity to Earth is explained because the Moon was made largely from Earth's mantle material and Thea's mantle, both of which share oxygen isotope signatures due to their formation in the same region of the solar system. The volatile depletion is explained because the extreme temperatures of the impact and the subsequent debris disk would have vaporized any volatile compounds. The small iron core is explained because the iron from both bodies merged with Earth's core. The angular momentum of the Earth-Moon system is consistent with the energy and geometry of a giant impact. By the mid-1980s, the giant impact hypothesis had become the standard model of lunar fusion. It has survived every major test, every new dataset, every computer simulation. It remains the best explanation we have. It is the story told in textbooks and documentaries and lectures around the world. But here is the problem that will not go away. The giant impact hypothesis explains how the Moon formed. It does not explain why the Moon has two faces. This is the central mystery. The question that ties together everything we have discussed so far and everything that follows. The giant impact gives us a Moon. It gives us the right composition, the right mass, the right angular momentum. But it gives us a symmetrical Moon with one face, not two, and the Moon, emphatically, has two faces. If the Moon coalesced from a uniformly mixed cloud of debris, a disk of vaporized and molten rock, swirling and cooling and clumping, with no preferred direction or orientation, it should have solidified into a roughly symmetrical body. The crust should have formed at approximately the same thickness everywhere, since the magma ocean that covered the newly formed Moon would have cooled under broadly similar conditions across its entire surface. The radioactive elements that generate internal heat should have been distributed more or less evenly. The volcanic eruptions that later punctured the crust should have occurred on both sides, not predominantly on one. But the Moon is not symmetrical. The near-side crust averages roughly 37 miles in thickness. The far-side crust averages roughly 50 miles and exceeds 60 miles in some regions. That difference, 13 miles or more of extra rock on the far side, is not subtle, it is enormous. 13 miles of additional crustal material represents a vast quantity of anorthositic rock, requiring either significantly more crystallization on one side of the magma ocean, or a large-scale redistribution of crustal material after formation. The asymmetry is not a minor anomaly, it is a fundamental feature of the Moon's architecture, detectable in gravity data, topography data, seismic data, and chemical composition data. It has been confirmed by every mission that has carried instruments capable of measuring it. The near side is enriched in creep, potassium, rare earth elements, and phosphorus, along with the radioactive heat-producing elements, thorium and uranium. This enrichment is concentrated in a region called the Procellarum creep terrain, which underlies much of the near side's volcanic terrain. The Procellarum creep terrain is enormous, roughly 2,000 miles across, covering a significant fraction of the near-side hemisphere. Gamma-ray spectrometers aboard the Lunar Prospector spacecraft mapped the distribution of thorium across the lunar surface with sufficient resolution to show that this element, one of the most reliable traces of creep material, is concentrated almost entirely on the near side. The far side is depleted in these elements, stripped of the radioactive heat sources that drove near-side volcanism for billions of years. The consequences of this chemical asymmetry cascade through every aspect of the Moon's geological history. On the near side, The concentrated radioactive elements acted as a slow-burning furnace in the mantle. Thorium-232, with a half-life of 14 billion years, and uranium-238, with a half-life of 4.5 billion years, have been generating heat through radioactive decay since the Moon formed. On the near side, where these elements are concentrated, the cumulative heat was sufficient to keep the mantle partially molten for billions of years, generating magma that rose through the thinner near-side crust and flooded the great impact basins, creating the Maria. On the far side, where these elements are depleted, the mantle cooled faster, solidified earlier, and produced little volcanism. The far side's thicker crust presented an additional barrier. Even if small amounts of magma were generated in the far side mantle, they had to penetrate through 50 or 60 miles of solid rock to reach the surface, compared to only 37 miles on the near side. In most cases, the magma solidified before it could break through. The result is the two-faced moon we observe. One hemisphere was volcanically active, geologically dynamic, repeatedly resurfaced by lava flows that buried the ancient terrain and created the smooth, dark plains visible from Earth. The other hemisphere was volcanically quiescent, geologically static, its original surface preserved nearly intact for more than 4 billion years. The near side has a young face, cosmetically altered by volcanism, its wrinkles and scars hidden beneath layers of dark basalt. The far side has an old face. Every crater visible, every impact recorded, every geological event preserved in the rock, exactly where it happened. The near side experienced billions of years of volcanism. The far side experienced almost none. The near side was resurfaced, smoothed, painted over by dark basaltic lava. The far side was left raw, cratered, ancient, exposed. And it gets worse. Because the asymmetry is not limited to the crust, the deep interior of the Moon is also asymmetric. The Grail mission, the Gravity Recovery and Interior Laboratory, consisting of twin spacecraft named Ebb and Flow that orbited the Moon in tandem, mapped the Moon's gravitational field with unprecedented precision between 2011 and 2012. The technique was elegant. By measuring the distance between the two spacecraft to within a fraction of a micrometer as they orbited the Moon together, scientists could detect tiny variations in the Moon's gravitational pull. When the leading spacecraft passed over a region with slightly more mass below the surface, it accelerated fractionally. The trailing spacecraft would accelerate a moment later as it passed over the same region. These infinitesimal speed changes, accumulated over thousands of orbits, produced a gravity map of the Moon that revealed its internal mass distribution in exquisite detail. What Grail found was profoundly uneven. Dense concentrations of material, called mascons, short for mass concentrations, sit beneath the Great Near-Side Mare basins. These mascons are among the most prominent gravitational anomalies in the solar system. Each one represents the dense basaltic lava that flooded the basin, plus, in some cases, upwellings of denser mantle material that rose through the thin crust and solidified beneath the lava fill. The mascons are so dense and so localized that they measurably deflect the orbits of spacecraft passing over them. Early lunar orbiters experienced unexpected orbital changes due to mascon perturbations, changes that puzzled mission controllers until the source was identified. The far side has its own gravitational anomalies, but they are distributed differently, reflecting a different geological history. Fewer lava-filled basins, less dense material near the surface, a thicker and more uniform crust. And beneath the South Pole Aitken Basin, the Moon's largest crater, sitting on the far side like a wound that never healed, lies the massive buried anomaly we discussed earlier, a concentration of excess mass weighing at least 2.18 quintillion kilograms, extending more than 300 miles below the surface. This mass is dense, denser than the surrounding mantle, suggesting it is metallic. It may be the remains of the asteroid that created the basin, its iron core embedded in the Moon's interior, like shrapnel from an ancient explosion. The Artemis II crew flew over this anomaly during their flyby, photographing the basin's eastern rim, where the ancient impact's devastation is still etched in the rock. They captured images of craters within craters, of fractured terrain, of the sharp knife-edged terminator where sunlight meets shadow without the softening blur of atmosphere. They observed color variations in the regolith, greens and browns that had not been highlighted by orbital instruments, subtle hues that may indicate compositional differences in the surface minerals, and they saw the impact flashes. 6 of them. 6 brief flickers of light in the darkness below, each one a meteoroid, a small rock from the spaces between the planets, striking the unprotected lunar surface at speeds of tens of thousands of miles per hour. Each flash was a reminder. The process that created the South Pole Aitken Basin, that scarred the far side beyond recognition, that buried a mountain of metal beneath the South Pole. That process is still active. It has not stopped. It has merely slowed. The bombardment continues, impact by impact, flash by flash, adding new craters to a surface that already has more craters than any other world we can study directly. What makes the crew's observation of these flashes particularly significant is that they detected them visually, with their eyes, not with instruments. The onboard camera systems, designed for wide-angle and telephoto surface photography, did not capture the flashes. This is not surprising. Impact flashes on the Moon are extremely brief, typically lasting less than 1/50th of a second, and they occur at unpredictable locations. A camera pointed at one area of the surface will almost certainly miss a flash that occurs elsewhere. The human eye, however, takes in the entire visual field simultaneously, and the human brain is exquisitely sensitive to transient changes in brightness. Detecting a brief flash against a dark background is precisely the kind of task at which human vision excels. A capability that evolved over millions of years in response to the survival advantages of noticing sudden movement and changes in the environment. Before this mission, impact flashes on the Moon had been observed only from Earth, using telescopes pointed at the night side of the near side during meteor showers. These Earth-based observations are limited by atmospheric conditions, by the requirement that the flash occur on the visible portion of the night side, and by the distance. 239,000 miles reduces even a significant flash to a barely detectable point of light. The Artemis II crew observed flashes from approximately 60 miles above the surface. At that distance, the flashes were unmistakable, vivid, sharp, and bright enough to be seen with the unaided eye. The crew's reports provide the first human testimony of impact flashes observed from lunar orbit and will help calibrate models of the impact flash luminous efficiency, the fraction of kinetic energy converted to visible light that are used to estimate impactor sizes from flash brightness. The lunar surface is an archive of this bombardment because there is no atmosphere to burn up incoming objects, no wind to erode the craters, no rain to wash them smooth, no rivers to cut through them, no plate tectonics to recycle the crust. The Moon preserves virtually every impact it has ever received. The craters on the far side span a continuous record stretching back more than 4 billion years. The oldest, most degraded craters record the earliest, most intense phase of bombardment, the late heavy bombardment, roughly 4 billion years ago, when a major reorganization of the outer planet's orbits scattered millions of asteroids and comets inward toward the Sun and the terrestrial planets. The freshest craters, bright, sharp-rimmed, with radiant ejector rays, record impacts from the recent geological past, perhaps the last few 100 million years. This archive is not just about the Moon. It is about Earth. Our planet was struck by the same population of impactors during the same period. The asteroids and comets that cratered the far side also struck Earth in proportional numbers. During the late heavy bombardment, Earth endured a rain of impacts that may have repeatedly vaporized its oceans, sterilized its surface, and reshaped its geology in ways we can barely imagine. Life emerged in this environment, somehow, or immediately after the bombardment subsided. Understanding the intensity, duration, and decline of the bombardment is critical to understanding the conditions under which life first appeared. But Earth does not preserve this record. Our dynamic planet has erased almost all evidence of the early bombardment. Of the roughly 190 recognized impact structures on Earth's surface, none predate about 2 billion years. The first 2.5 billion years of Earth's impact history, the period that overlaps with the late heavy bombardment and the origin of life, is gone, subducted, eroded, recycled, lost. The mechanisms of this loss are relentless. plate tectonics, the process by which Earth's lithosphere is divided into rigid plates that move, collide, and subduct beneath each other, continuously destroys old oceanic crust by pulling it down into the mantle at subduction zones. No oceanic crust on Earth is older than about 200 million years. Continental crust persists longer, but even on continents, erosion by wind, water, ice, and chemical weathering gradually removes surface features. A crater 100 miles across might survive on Earth for a few 100 million years before erosion and sedimentation render it unrecognizable. On the Moon, that same crater survives for 4 billion years, its form degraded slowly by smaller impacts and the microerosion of the solar wind, but fundamentally intact, readable, datable. The contrast is stark. Earth is a planet that destroys its own history. The Moon is a world that preserves it. This is not a failure of Earth or a virtue of the Moon. It is simply a consequence of the geological processes that operate on each body. Earth's dynamism makes it habitable. Plate tectonics recycles carbon, regulates climate, generates magnetic fields, builds continents, creates the conditions for life. But it also erases the record of the past with merciless efficiency. The Moon's quiescence makes it uninhabitable, but also makes it an archive. The same geological inactivity that prevented life from arising on the Moon also prevented the Moon from losing its earliest history. We need both worlds, one to live on, one to remember for us. It is preserved on the Moon, especially on the far side, where no volcanic resurfacing has buried the ancient craters, where no geological activity has disturbed the surface. The far side is a time capsule of the inner solar system's violent infancy, a frozen record of the environment in which life on Earth was born. But here's what makes this truly terrifying. The bombardment that created this record has not ended. Those 6 flashes the Artemis II crew saw were not echoes of the past. They were the present tense. Meteoroids are striking the Moon right now, at this moment, as these words reach your ears. They are also striking Earth. The difference is that we have an atmosphere to incinerate the smallest ones and pure statistical luck to protect us from the largest. The Moon has neither. It receives every impact at full speed, without mitigation, without mercy. Every crater on the far side is a reminder that the solar system is not safe. It is a shooting gallery, and we live in it, protected by a thin shell of air and a modest magnetic field, in a brief window of relative calm that could end at any time. Not because the universe is malicious, but because it is large and full of debris and utterly indifferent to the fragile patterns of biology that have briefly flourished on one small blue world orbiting an ordinary star. The question of why the Moon's far side looks so radically different from its near side has been one of the defining puzzles of planetary science for more than 6 decades. At least 5 major theories have been proposed, debated, tested against data, refined, and in some cases partially discarded. Each theory illuminates a genuine piece of the puzzle. Each captures something true about the Moon. And each, when examined against the full body of evidence now available, leaves critical questions unanswered. The search for a complete explanation is ongoing, and it is more active now, in the wake of Artemis II and the Chang'e sample return, than at any point since the Apollo era. The first and most straightforward explanation is the tidal hypothesis. It rests on a simple physical observation. In the earliest period after the Moon's formation, the Moon was much closer to Earth than it is today. Current orbital mechanics models, run backward through time, indicate that the Moon may have orbited as close as a few Earth radii from the surface, perhaps 15,000 to 20,000 miles, compared to the roughly 239,000 miles that separate the two bodies now. To put this in perspective, the International Space Station orbits at approximately 250 miles above Earth's surface. The early Moon may have been only 60 to 80 times farther out than the space station is now. Seen from Earth's surface, if there had been anyone to look, the Moon would have appeared enormous, filling a significant portion of the sky, looming over the molten landscape like an eye. At that close range, tidal forces from Earth would have been enormous. Tidal force scales with the inverse cube of distance, meaning that halving the distance between two bodies increases the tidal force by a factor of 8. At 15,000 miles, the tidal force on the Moon would have been roughly 4,000 times stronger than it is at today's distance. The moon would have been distorted, stretched along the line connecting its center to Earth's center, and the internal friction generated by this tidal flexing would have produced heat. The key insight is that this tidal heating would not have been perfectly uniform across the moon's interior. Research published in 2018 by Alice Quillian and her colleagues at the University of Rochester quantified this asymmetry. They calculated that tidal heating per unit area in a lunar crustal shell would have been 10 to 20% higher on the near side than on the far side, due to what physicists call the octupole moment in Earth's tidal field. The octupole moment is a higher-order gravitational effect that arises because the moon is not infinitely far from Earth. The difference in gravitational strength between the near and far sides of the moon is not negligible, and this difference creates a slight asymmetry in the tidal heating pattern. More heat on the near side, less heat on the far side. Over millions or tens of millions of years of crustal formation, this 10 to 20% difference could have meaningful consequences. More heat on the near side means the magma ocean there cooled more slowly, which means the crust that formed from the crystallizing magma ocean grew more slowly on the near side. A slower growing crust is a thinner crust, and a thinner crust has profound geological consequences. It means magma from the underlying mantle has less rock to push through in order to reach the surface. Volcanic eruptions become more likely. Lava flows become more extensive. Over billions of years, the near side accumulates more volcanic material, creating the dark maria we see today. The numbers are striking. A seemingly modest 10 to 20% difference in heating, sustained over the timescale of magma ocean crystallization, can produce a measurable difference in crustal thickness between the two hemispheres. But the tidal hypothesis has a weakness that prevents it from being a complete explanation. It predicts a gradual, smooth transition between the thin near-side crust and the thick far-side crust, a gentle gradient in crustal thickness that mirrors the gentle gradient in tidal heating. What Grail and other missions actually observe is a transition that is more abrupt than the tidal model predicts. The boundary between the creep-enriched thin crust of the near side and the creep-depleted thick crust of the far side is relatively sharp, concentrated in a region that does not perfectly align with the expected tidal heating pattern. Something beyond tidal forces must have been at work. The second theory, the magma ocean crystallization model, takes the story deeper into the moon's formative era. When the moon first coalesced from the debris of the giant impact, its entire surface was covered by a global ocean of molten rock, a magma ocean that may have been 400 miles deep or more. This is not speculation. The existence of the magma ocean is well established by the mineralogy of the lunar highlands, which are composed primarily of anorthophosite, a rock type that forms when plagioclase feldspar crystals float to the top of a cooling body of silicate melt. The highlands are, in essence, a solidified froth of feldspar that rose to the surface of the magma ocean and accumulated there as the ocean crystallized from the top down and the bottom up over tens of millions of years. The magma ocean crystallization model proposes that if the cooling rate of this ocean was different on the near and far sides, the resulting crust would have been different as well. The mechanism for differential cooling is the thermal influence of Earth itself. In the immediate aftermath of the giant impact, Earth was not a temperate, blue-green world. It was a hellscape, its surface largely molten, radiating enormous amounts of thermal energy in the form of infrared radiation. The near side of the moon, facing this molten Earth from only a few thousand miles away, would have been bathed in Earth's thermal glow. This extra heat would have slowed the cooling of the magma ocean on the near side, while the far side, facing away from Earth into the cold of space, cooled faster. Faster cooling means faster crystallization, which means more feldspar floating to the surface per unit time, which means a thicker crust forming on the far side. This model makes the asymmetry primordial, a feature built into the moon's very first geological structures, present from the beginning rather than imposed later by external events. It has the appeal of simplicity and the support of thermal physics, but it struggles with a specific distribution of creep elements across the lunar surface. Creep, potassium, rare earth elements, and phosphorus represents the last liquid to crystallize from the magma ocean. As the ocean cooled and solid minerals formed, the elements that did not easily fit into the crystal lattices of common minerals, the so-called incompatible elements, became increasingly concentrated in the remaining liquid. This process, called fractional crystallization, is well understood from terrestrial geology. It is the same process by which granitic magma on Earth becomes progressively enriched in silica and rare elements as crystallization proceeds. On the Moon, the process operated on a global scale, concentrating incompatible elements into a residual liquid layer that represented perhaps the last 5 to 10% of the original magma ocean's volume. By the time the magma ocean was nearly fully solidified, the last dregs of liquid were intensely enriched in creep. These dregs should have been distributed relatively evenly across the Moon's subsurface, sandwiched between the floating feldspar crust above and the settled dense minerals below. But creep is not evenly distributed. It is concentrated on the near side, in the procellarum creep terrain, a roughly circular region underlying much of the Moon's most volcanically active terrain. This concentration is not centered on the sub-Earth point where Earth's thermal radiation would have been strongest during the magma ocean era. It is offset to the northwest, overlapping with Oceanus Procellarum. Simple differential cooling cannot explain this specific spatial distribution. Something else must have moved the creep from its original, more uniform location to its present concentrated one. The third theory is the companion moon hypothesis, and it is the most creative of the classical models. Proposed by Martin Jutzi and Eric Asfaug and published in Nature in 2011, it imagines a scenario in which the giant impact that created the Moon also produced a smaller companion, a second, much smaller moon that co-orbited with the primary moon for millions of years before eventually colliding with it. The idea has an appealing audacity. It proposes that for a brief period in the solar system's early history, Earth had two moons, not one, two. The primary moon, the large one, essentially the moon we know, and a smaller companion, perhaps a few hundred miles across, sharing the same orbital space. The two bodies would have been gravitationally linked, orbiting Earth in a cosmic dance that lasted millions of years before destabilizing. The physics of giant impacts allows for this possibility. When a Mars-sized body strikes the proto-Earth, the resulting debris disk can fragment into multiple clumps, some of which may grow large enough to be gravitationally stable. A companion moon might have survived in a Trojan orbit, a gravitationally stable point 60 degrees ahead of or behind the primary moon in its orbit, for tens of millions of years before. Perturbations from the Sun or other bodies destabilized its position. When the companion finally collided with the primary moon, it would have been a low-speed impact, perhaps only a few thousand miles per hour, because both bodies were in similar orbits. At that speed, the companion would not have created a crater. It would have splattered across one hemisphere, adding a thick layer of new material to that side. Jutzi and Asfaug's simulations showed that this scenario could produce a crustal thickness asymmetry consistent with what we observe. Several miles of extra material on one side, matching the difference between the near side and far side crust. The model was widely discussed and attracted significant attention because of its novelty and its ability to address the crustal thickness problem directly. But the companion moon model has significant weaknesses. A low-speed collision between two bodies should produce compositional anomalies at the boundary, where the companion's material meets the primary's original surface. The companion, having formed from a different part of the debris disk and having experienced a different thermal history, would not be chemically identical to the primary moon. Where the two materials meet, there should be a detectable chemical discontinuity, a sharp change in elemental abundances that would show up in orbital spectroscopy data. These anomalies have been searched for extensively using data from the Clementine, Lunar Prospector, and Lunar Reconnaissance Orbiter missions. They have not been found. The Moon's composition varies gradually and smoothly across its surface, which is inconsistent with a discrete layer of foreign material deposited by a companion's impact. Additionally, the companion moon model does not naturally explain the creep distribution. Adding material to the far side would dilute creep there, but it would not concentrate creep on the near side. The near side enrichment requires a mechanism that actively moved creep material from one hemisphere to the other, and the companion moon model provides no such mechanism. The model addresses the crustal thickness problem elegantly, but creates new problems in the process. Problems that, as of this recording, remain unresolved. There is also the question of detectability. If a companion moon existed, its formation and destruction should have left gravitational, mineralogical, and seismic signatures in the moon's internal structure. The Grail mission, with its exquisitely sensitive measurements of the moon's gravity field, detected no clear evidence of a buried compositional boundary consistent with a companion moon accretion event. Seismic data from the Apollo-era lunar seismometers, instruments that recorded moonquakes and meteoroid impacts for 8 years on the near side, revealed a layered interior but no obvious discontinuity at the depth where a companion's material would have been added. The absence of these expected signatures does not definitively rule out the companion moon theory, but it places significant constraints on the size, composition, and impact geometry of any hypothetical companion, narrowing the range of viable scenarios considerably. It is worth pausing here to observe something about the state of this scientific question. We have 3 theories: tidal heating, magma ocean crystallization, and companion moon accretion, each of which explains part of the asymmetry, but fails to explain the whole. This is not a failure of science. It is science at its most characteristic. The universe is not obligated to be explicable by a single, elegant mechanism. The moon's asymmetry may well be the result of multiple processes acting in concert. Tidal effects shaping the magma ocean's cooling rate, differential crystallization producing initial thickness variations, a companion collision adding additional material, all of these stacked on top of each other and modified by subsequent events. The real moon is messier than any single model. The challenge is not to find the one correct theory, but to determine how much of the asymmetry each process contributed and how they interacted over the hundreds of millions of years during which the moon's fundamental structure was being established. The 4th theory, the South Pole Aitken Basin redistribution model, addresses this directly. Published in 2022 by Matt Jones and colleagues at Brown University in the journal Science Advances, this theory focuses not on the moon's formation, but on a specific event that occurred roughly 700 million years later, the catastrophic impact that created the South Pole Aitken Basin. To understand this theory, you need to understand the sheer scale of the South Pole Aitken impact. This was not a large crater being formed, this was a planetary-scale catastrophe. The impactor, estimated at more than 100 miles in diameter, travelling at speeds of perhaps 25,000 to 40,000 miles per hour, struck the far side of the moon with enough energy to excavate a basin stretching more than 1,500 miles across and punching more than 8 miles into the crust and upper mantle. The impact liberated more energy than the combined nuclear arsenals of every nation on Earth, multiplied by a factor of millions. The shock wave propagated through the moon's entire interior, reflecting off the core mantle boundary, constructively interfering at the antipodal point on the near side, and temporarily liquefying vast volumes of mantle rock. The key idea is that the impact did far more than excavate a crater. It generated a thermal plume, an enormous wave of superheated material that propagated through the moon's interior, from the impact site on the far side to the antipodal region on the near side. As this plume moved through the mantle, it swept up the creep material that had been distributed more or less uniformly beneath the moon's surface. The plume deposited this material preferentially on the near side, concentrating it in a region that roughly corresponds to the Procellarum creep terrain. The physics of this transport mechanism are worth understanding, because they illustrate how a single event can reshape a world's entire geological trajectory. When the South Pole Aitken impactor struck the far side, it converted its kinetic energy into thermal energy in a fraction of a second. The immediate vicinity of the impact was vaporized. A wider region was melted, An even wider region was heated significantly above its ambient temperature. This thermal anomaly, a vast superheated zone centered on the impact site, began to propagate through the moon's interior. Hot material is less dense than cool material. It rises. The superheated mantle beneath the impact site rose upward and spread outward, flowing through the moon's interior like a wave in a fluid, seeking equilibrium. But the moon is not a simple, uniform fluid. It is a layered body with a solid crust, a partially crystallized mantle, and a small iron core. The thermal plume from the South Pole Aitken impact had to navigate this layered structure, and as it did, it interacted with the creep-enriched residual layer that had been sandwiched between the crust and the mantle since the magma ocean crystallized. The plume, being hotter and more buoyant than its surroundings, rose toward the base of the crust and spread laterally. As it spread, it entrained the creep material, carrying it along like a river carrying sediment. The plume's energy was not infinite. It dissipated as it traveled, losing heat to its surroundings. But the simulations show that a plume generated by an impact of the right magnitude could retain enough energy to transport creep material across the moon's full diameter. From the far side impact, sight to the antipodal region on the near side, before finally dissipating. Jones and his team ran extensive computer simulations modeling the thermal evolution of the moon's interior following the impact. Their results showed that a plume of the right size and energy, generated by an impactor of the right mass striking at the right angle, could transport sufficient creep material across the moon's interior to produce the observed enrichment pattern on the near side. The concentrated creep material, being rich in radioactive elements thorium, uranium, potassium, then acted as a long-term heat source, keeping the near side mantle warmer than the far side mantle for billions of years. This sustained thermal anomaly promoted partial melting, generated magma, and drove the volcanism that created the near side Maria. The far side, meanwhile, was depleted. Stripped of its creep material by the plume, the far side mantle cooled faster, solidified earlier, and produced little or no volcanism. Its ancient highlands were preserved, essentially untouched, while the near side was being resurfaced by volcanic eruptions driven by the concentrated heat of radioactive decay. The elegance of this model is remarkable. It connects two of the moon's most prominent features, the near side Maria and the far side highlands, through a single ancient catastrophe. The two faces of the moon are not independent accidents. They are consequences of the same event, linked by a thermal plume that redistributed the moon's internal chemistry in a matter of hours or days, setting the conditions for billions of years of divergent geological evolution. Consider the implications. A single asteroid striking the far side 4.25 billion years ago may have determined the geological destiny of both hemispheres for the remaining 4 billion years of the moon's history. One impact, one event, one cascade of physical consequences that rippled through the moon's interior and established the chemical asymmetry that governs everything, where volcanism occurs, where the crust is thin, where the Maria form, which face shows smooth dark plains to Earth, and which face preserves the ancient highlands in pristine isolation. If this model is correct, and the evidence for it has grown steadily since its publication, then the moon's two faces are ultimately the product of a single rock, tens of miles across, hitting the surface at just the right angle, at just the right speed, in just the right place, at just the right time. The moon's identity was decided by a collision that lasted less than a minute. But the model is not without limitations. The simulations require precise initial conditions. The impactor must strike at a specific angle, at a specific speed, with a specific mass. Small changes in these parameters can produce dramatically different outcomes. Plumes that are too weak to transport creep, or too strong, dispersing it uniformly rather than concentrating it. The real moon, shaped by real physics with all its messiness and contingency, may not have experienced the exact conditions that the idealized simulations require, and the model does not fully explain the sharp, well-defined boundaries of the procellarum creep terrain, or the specific pattern of individual mare basins that erupted within it. The fifth body of evidence, and the one most actively reshaping the field as of this recording, comes from the first physical samples ever retrieved from the moon's far side. On June 25, 2024, China's Chang'e 6 mission returned 1,935.3 grams of lunar soil and rock to Earth from the South Pole Aitken Basin. The samples were collected from the Apollo Basin, a smaller crater nested within the larger South Pole Aitken structure, by a robotic lander that used both a surface scoop and a subsurface drill. The material was loaded into an ascender module, launched to lunar orbit, transferred to a return capsule, and sent on a 53-day journey back to Earth. It was, quite literally, the first time any mission in the history of space exploration had brought back material from the far side of the Moon. The results are reshaping our understanding of lunar history. Radiometric dating of basalt fragments in the Chang'e 6 samples, published in the journal Science, revealed that volcanism occurred on the far side roughly 2.83 billion years ago, approximately 1.4 billion years after the South Pole Aitken Basin impact, and nearly 2 billion years after the Moon itself formed. This was unexpected. The far side was supposed to be dead, geologically quiescent, its creep-depleted mantle too cool to generate significant volcanism. But here were volcanic rocks, unambiguously dated, erupted from a mantle source that was chemically distinct from anything sampled by the Apollo missions on the near side. The significance of this finding is difficult to overstate. Before Chang'e 6, every volcanic rock in the lunar sample collection came from the near side, from the Apollo and lunar landing sites, all located within or near the Procellarum creep terrain. These samples showed that near-side volcanism was driven by the concentrated radioactive heat of creepy elements, producing titanium-rich, incompatible element-enriched basalts from a mantle source that was warm, relatively wet, and chemically fertile. The entire framework of lunar volcanic theory was built on near-side samples. The assumption was that the far side, lacking creep, lacked the thermal engine to produce volcanism. Chang'e 6 demolished this assumption. The far side basalts are low titanium, depleted in incompatible elements, and contain almost no creep component. Their source mantle was dry, significantly lower in water content than the near side mantle, as later analysis would confirm. And yet, volcanism occurred. The explanation proposed by the study's authors is that the thin crust beneath the South Pole Aitken Basin, thinned by the enormous impact that excavated it, provided a pathway for deeper mantle material to reach the surface even without the extra heat from radioactive elements. The basin acted as a wound, a permanent thin spot in the Moon's crustal armor through which small amounts of magma could seep for billions of years after the initial impact. This finding has implications that extend far beyond the Moon. It demonstrates that impact basins can act as long-lived volcanic conduits, pathways that allow mantle material to reach the surface of a rocky body, even in the absence of other thermal drivers. On Earth, volcanic activity is driven primarily by plate tectonics and mantle plumes, processes that are powered by Earth's substantial internal heat. On the Moon, where internal heat is far more limited, the South Pole Aitken Basin apparently provided an alternative mechanism, a structural weakness in the crust that compensated for the absence of thermal energy. This mechanism may operate on other bodies in the solar system as well. Mars has its own giant impact basins, Hellas, Argea, Isidis, and some of these basins show evidence of volcanic activity that postdates their formation by billions of years. The Moon may be showing us a general principle, that giant impacts create not only craters, but also long-lived volcanic pathways that shape a world's geological evolution for billions of years after the original event. And it gets stranger. The Chang'e 6 samples also revealed that the far side basalts were erupted from a mantle source that had a different isotopic composition from the near side mantle, not just different chemistry, but different ratios of certain isotopes that trace the Moon's earliest differentiation processes. This suggests that the near side and far side mantles have been chemically isolated from each other since very early in the Moon's history. Perhaps since the magma ocean itself was crystallizing. The Moon's interior is not just asymmetric, it is compartmentalized. In July of 2025, Chinese scientists announced 4 landmark discoveries based on further analysis of the Chang'e 6 material, published as cover articles in the journal Nature. They precisely dated the formation of the South Pole Aitken Basin at 4.25 billion years ago, making it one of the oldest datable impact events in the solar system, and confirming that the basin formed within the first 300 million years of the Moon's existence, when the magma ocean was still cooling and the fundamental structures of the lunar interior were still being established. They detected evidence of an ancient magnetic field on the far side, with a possible rebound in field intensity around 2.8 billion years ago, a finding that complicates models of the lunar dynamo, the mechanism by which the Moon's small iron core generated a magnetic field. The rebound, if confirmed, would suggest that the dynamo did not simply wind down steadily but experienced fluctuations, possibly driven by changes in core crystallization rate or by mantle convection events triggered by the concentrated creep heating on the near side. They also confirmed that the far side mantle is significantly drier than the near side. Water, in the form of hydroxyl groups chemically bound into the crystal structures of mantle minerals like olivine and pyroxene, affects nearly every aspect of mantle behavior. It lowers melting temperatures, reduces viscosity, increases the likelihood of volcanic eruptions, and influences the rate at which magma rises through the crust. A dry mantle is a stiff mantle, harder to melt, slower to flow, less likely to produce volcanism. The confirmation that the far side mantle is drier than the near side provides a physical mechanism for the far side's geological quiescence that is independent of, but complementary to, the creep depletion. The far side was doubly disadvantaged. It lacked the radioactive heat sources to warm its mantle, and it lacked the water that would have made melting easier, even at lower temperatures. And they characterized the physical and mineralogical properties of far side regolith, finding it to be more cohesive, clumpier, stickier than near side material, with finer and more irregular particles shaped by billions of years of impact reworking in the absence of volcanic resurfacing. Mahesh Anand, a professor at the Open University in the United Kingdom, summarized the impact of these findings with striking candor. The Changi 6 results, he said, are turning many well-established hypotheses and theories in lunar science upside down, necessitating the re-examination of many of those theories. This is not the language of incremental progress. This is the language of paradigm shift. The significance of Anand's statement lies in its context. Lunar science is a mature field. The basic framework of lunar geology has been in place since the Apollo era. Textbooks have been written and revised and written again. University courses have been taught. Careers have been built on the near-side sample data and the orbital measurements that supported it. For a senior researcher to say that well-established theories are being turned upside down is not a casual observation. It reflects a genuine upheaval in the field, a recognition that the first physical samples from the far side have revealed a world that the near-side calibrated models did not predict and cannot fully explain. The far side mantle should not have been able to produce volcanism. It did. The far side basalts should have resembled near side basalts, at least approximately. They do not. The far side regolith should have had similar physical properties to near side regolith. It does not. Each prediction failed. Each failure demands a revision to the underlying theory. And it is in this context that the Artemis 2 flyby takes on its full significance. The crew's observations complement the sample data in ways that neither could achieve alone. Their photographs of color variations across the far side may correlate with compositional boundaries that the Changi 6 samples can help calibrate. Their impact flash observations provide data on the current meteoroid environment. Their detailed descriptions of the terminator and the terrain along South Pole Aitken Basin's rim offer contexts that orbital imagery, however high resolution, cannot fully replicate. The crew saw greens and browns in the regolith that orbital instruments had not highlighted. They described the terminator in language that conveyed not just geometry but meaning. Victor Glover calling it magical, describing islands of light and valleys like black holes. Christina Koch documented fractures and texture variations visible only under the specific lighting conditions of the flyby. Jeremy Hansen operated cameras at focal lengths of 400 millimeters, producing close-up images of individual craters with detail and context that will take years to fully analyze. These observations may seem subjective, the impressions of human beings rather than the measurements of instruments, but this underestimates the power of human perception. The human visual system processes color, texture, spatial relationships, and contextual anomalies in ways that camera systems and spectrometers cannot replicate. When the crew reported greens and browns in the regolith, they were detecting subtle color differences, likely caused by variations in mineral composition, space weathering state, or particle size that had been averaged out in orbital imagery. The human eye, viewing the surface under the specific solar angle of the flyby trajectory, with the specific shadow geometry of the terminator nearby, could distinguish hues that orbital sensors, integrating light over different angles and times, had blurred into uniformity. This is why crude exploration remains scientifically valuable, even in an era of increasingly capable robots. Human observers notice what they do not expect. Instruments measure what they are programmed to measure. The gap between these two capabilities is where discovery lives. The crew also observed the far side's terrain with the kind of intuitive geological judgment that comes from years of field training. Christina Koch had spent extensive time at terrestrial analog sites, studying volcanic and impact terrains in Iceland, the Canadian Shield, and the American Southwest. Her descriptions of the far side's surface textures, the way certain craters appeared to have been formed in material with different mechanical properties than others, the way ejecta blankets, varied in roughness and reflectivity, carry information that will be correlated with orbital data and used to refine geological models of far-side regolith evolution. And then there was the solar eclipse. As Orion emerged from behind the moon, the sun disappeared behind the lunar disk, and the crew witnessed a total solar eclipse from a vantage point that no human had ever occupied. The totality lasted nearly 54 minutes, an impossibly long duration compared to the few minutes of totality possible during a solar eclipse viewed from Earth's surface. The reason for this extreme duration is geometry. On Earth, the moon's shadow sweeps across the surface at more than 1,000 miles per hour, and any given location experiences totality for only a few minutes at most because the shadow passes quickly. But the Artemis II crew were not standing still on a surface being swept by a shadow. They were orbiting alongside the moon, moving at roughly the same angular rate, which kept them in the moon's shadow for nearly an hour. It was as if they were riding inside the shadow itself, traveling with it, rather than waiting for it to pass over them. During those 54 minutes, the crew observed the sun's corona, the outermost layer of the solar atmosphere, glowing as a luminous ring around the darkened moon. The corona is normally invisible from Earth, overwhelmed by the brilliance of the sun's photosphere. It becomes visible during total solar eclipses, but only for the brief moments of totality. The Artemis II crew had 54 minutes to study it, an unprecedented observational window that allowed them to document the corona's structure in detail impossible from Earth. They described the corona's wisps as baby hairs, delicate filaments of superheated plasma extending outward from the sun's disk. These filaments are shaped by the sun's magnetic field, tracing the invisible lines of force that arch outward from the solar surface and extend millions of miles into space. The science community is still analyzing these observations, investigating whether the glow included contributions from zodiacal light, sunlight scattered by interplanetary dust, as well as the corona itself. And in the darkness of totality, with no sun and no Earth visible, the crew reported seeing bright planets, Mars, Venus, and Saturn, alongside stars that are normally invisible during lunar observation. They were seeing the solar system stripped bare, from behind the moon, during an eclipse, in the deepest silence any human being has ever experienced. And on the surface below, they saw the meteoroid flashes, 6 brief, bright flickers of creation and destruction, playing out in real time on an ancient stage. Here is what we now know, assembled from 67 years of orbital observation, 383 kilograms of near-side samples, roughly 2 kilograms of far-side samples, 2 robotic far-side landings, and 1 crewed flyby. And here is why it matters far more than most people realize. The moon is not a dead rock. It is not a static, unchanging body, drifting passively through space beside us. It is a record a 4.5 billion year old stone tablet inscribed in a language of craters, lava flows, fractures, chemical gradients, buried anomalies, and preserved surfaces. Every feature on the moon records an event. Every crater records an impact. Every lava flow records an eruption. Every chemical signature records a process. Crystallization, melting, degassing, irradiation that occurred at a specific time and under specific conditions. And the far side, the hemisphere that permanently faces away from Earth, hidden from every telescope and every naked eye on our planet, contains the most important chapters of that record. These are the chapters that have been protected by their own isolation, preserved by the absence of the geological resurfacing that buried so much of the near side's ancient history beneath layers of basaltic lava. The far side highlands are the moon's original surface, or as close to it as any surface in the solar system that we can access directly. They have been sitting in the vacuum of space, unchanged except by the slow accumulation of new impact craters and the subtle effects of space weathering, for more than 4 billion years. Let that sink in. The rocks beneath the Artemis 2 cruise trajectory were older than any rock on Earth, older than the oldest fossil, older than the oldest intact geological formation, older than the continents, older than the oceans, older than the atmosphere in its current form. The far side surface dates back to the solidification of the lunar magma ocean, roughly 4.4 billion years ago. Nothing on Earth's surface is that old. Our planet's geological dynamism has recycled, remelted, and reformed its surface materials many times over. The moon's far side has not. It is the closest thing in the accessible solar system to a preserved snapshot of what the inner solar system looked like in its first few 100 million years. To walk on the far side, as future Artemis crews may one day do, would be to walk on a surface that predates everything familiar about Earth. The first rocks that a far side astronaut would pick up would have formed before the first continent existed, before the first ocean filled, before the first raindrop fell, before the first microbe divided, before the atmosphere contained any oxygen at all. These rocks have been sitting on the surface, exposed to the vacuum of space, irradiated by the solar wind, struck by micrometeoroids, slowly darkened by space weathering, for longer than any terrestrial geological process has been operating. They are older than life. They are nearly as old as the solar system itself. The craters that cover the far side span a continuous timeline of bombardment. The oldest and most degraded ones, barely recognizable as craters, their rims eroded by smaller impacts, their interiors filled with pulverized debris, date from the late heavy bombardment, roughly 4.1 to 3.8 billion years ago. This was a period of dramatically increased impact rates across the inner solar system, triggered by what planetary scientists believe was a major orbital migration of the giant planets. Jupiter and Saturn shifting their positions, gravitationally scattering enormous numbers of asteroids and comets from stable orbits into chaotic trajectories that crossed the paths of the terrestrial planets. The theoretical framework for this orbital migration is called the Nice model, named after the city in France where it was developed. First published in 2005 by Rodolfo Gomes, Hal Levison, Alessandro Morbidelli, and Cleomenes Tiganis, the Nice model proposes that the outer planets, Jupiter, Saturn, Uranus, and Neptune, formed in a more compact configuration than they currently occupy, and that gravitational interactions among them caused a cascading instability that sent the planets migrating outward. As the planets moved, they gravitationally disturbed the vast population of small bodies, asteroids and comets, that orbited in the spaces between them, flinging millions of objects inward toward the Sun. The inner solar system became a shooting gallery. The terrestrial planets, Mercury, Venus, Earth, and Mars, and the Moon were all subjected to a spike in the bombardment rate that lasted hundreds of millions of years. Earth was hit by these same objects. The same asteroids and comets that scarred the far side also struck Earth, Mars, Venus, and Mercury. The impacts were proportional to each body's gravitational cross-section. Earth, being larger and more massive, attracted more impactors than the Moon. During the worst of the bombardment, Earth may have experienced impacts large enough to vaporize portions of its ocean, sterilize its surface to significant depth, and fundamentally alter its atmospheric chemistry. Some scientists have argued that the bombardment was so intense that life could not have survived it, that any early organisms would have been destroyed, and life must have arisen only after the bombardment subsided, roughly 3.8 billion years ago. Others have argued that life may have found refuge in deep subsurface environments, surviving the bombardment in the cracks and pores of rock far below the reach of even the largest impacts. The debate is not settled, the data is insufficient, and this is exactly why the far side matters. The lunar impact record, the chronology of craters preserved on the far side highlands, is our best and most complete archive of the bombardment that shaped Earth during the critical period when life first appeared. Earth has lost this record, the Moon has kept it. Every crater on the far side is a data point in the story of Earth's earliest history. Studying these craters, their sizes, their degradation states, their spatial distribution, their relationship to each other, allows scientists to reconstruct the intensity of the bombardment over time, calibrate the ages of planetary surfaces throughout the solar system, and constrain the environmental conditions under which life on Earth first emerged. The connection between the Moon's cratering record and the origin of life on Earth may seem surprising. What does a crater on the far side of the Moon have to do with the first living cell on Earth? The answer is context. Life requires stable conditions, a sustained period during which liquid water can persist on a planet's surface, complex organic molecules can accumulate, and chemical reactions can proceed without being interrupted by impacts large enough to vaporize the ocean or melt the crust. If the bombardment was intense enough, these conditions did not exist until it subsided. The far side cratering record tells us exactly when the bombardment became mild enough for life to gain a foothold, and therefore, in a very real sense, tells us when life on Earth became possible. This is not science fiction. This is the geological record of our own origins, preserved on a world 239,000 miles away, sitting in plain view, or what would be plain view if we could see the far side from Earth, waiting for anyone with the will to go there. The methodology that makes this record readable is called crater counting chronology, and it is one of the most powerful tools in planetary science. The principle is deceptively simple. Older surfaces have more craters than younger surfaces, because they have been exposed to the rain of impactors for longer. By counting the number of craters on a given area of surface, and by measuring their sizes and degradation states, scientists can estimate the age of that surface. The technique was calibrated using the Apollo samples, rocks whose ages were measured precisely by radiometric dating in laboratories on Earth. By correlating the radiometric ages of rocks from specific Apollo landing sites with the crater densities at those same locations, scientists established a mathematical relationship between crater counts and surface age. This relationship, the lunar crater chronology function, is now used to estimate the ages of surfaces across the entire Moon, and by extension, across every rocky body in the inner solar system. But the calibration has gaps. The Apollo missions sampled only 6 locations, all on the near side, spanning a limited range of ages. The oldest reliably dated Apollo samples are roughly 4.1 billion years old. The youngest are roughly 3.1 billion years old. Between 3.1 billion years ago and the present, there are no calibration points. The ages of young surfaces must be extrapolated using assumptions about the rate at which the impactor flux has declined over time. And before 4.1 billion years ago, calibration is even more uncertain, because the oldest surfaces have been so heavily cratered that individual impacts become difficult to distinguish. The entire edifice of planetary chronology, the system by which we assign ages to the surfaces of Mars, Mercury, and the moons of the outer planets, rests on a calibration that is anchored by fewer than a dozen data points, all from one hemisphere of one world. The Chang'e 6 samples added a critically important new calibration point, 2.83 billion years ago, from the far side. The Chang'e 5 samples, returned from the near side in December 2020, had already provided another 2 billion years ago from the Oceanus Procellarum region. These new data points are filling in the gaps in the chronology function, improving the precision of age estimates for surfaces across the solar system. but significant gaps remain. The period between 3.8 and 4.2 billion years ago, the era of the late heavy bombardment itself, is still poorly calibrated, precisely because the surfaces that date from this era are so saturated with craters that counting becomes ambiguous. The far side, with its ancient highlands, is the best place to resolve this ambiguity. It is the Rosetta Stone of planetary chronology. Let that sink in. The answer to one of the deepest questions in biology, when and how did life begin on Earth, may depend in part on the cratering record of the Moon's far side. The far side also holds clues to the Moon's internal evolution that are only now being decoded. The Chang'e 6 samples revealed that the far side mantle is chemically distinct from the near side mantle in at least 3 important ways. It is depleted in creep elements. It is depleted in water, the hydroxyl groups that are chemically bound into mantle minerals, and that affect melting temperatures, magma viscosity, and volcanic behavior. And it produced volcanism that was chemically different from near-side volcanism. Low titanium basalts from a depleted source erupted through a crust that was thin enough to serve as a pathway, despite the absence of the radioactive heating that drove near-side eruptions. These differences tell us that the Moon's interior is not homogeneous. It is zoned, layered, and fundamentally asymmetric, with a compositional geography that mirrors the surface geography visible from space. The near-side mantle is hot, wet, relatively speaking, and creep-enriched. The far-side mantle is cooler, drier, and creep-depleted. This internal asymmetry was likely established by the thermal plume from the South Pole Aitken impact, and it has persisted for 4 billion years, shaping every subsequent chapter of the Moon's geological story. What makes this persistence remarkable is the scale of time involved. 4 billion years. For 4 billion years, the Moon has maintained a chemical gradient across its interior, one hemisphere enriched, the other depleted, without convective mixing homogenizing the difference. On Earth, mantle convection stirs the interior continuously, cycling material from surface to core and back again over hundreds of millions of years. No chemical asymmetry of this magnitude could persist in Earth's dynamic interior for even a fraction of the time it has persisted in the Moon's. The Moon's interior is too cool, too viscous, too sluggish for large-scale convection. The chemical asymmetry established 4 billion years ago is still present today, frozen in place, preserved, like everything else about the Moon, by the absence of the geological processes that erase evidence on more active worlds. This is a profound insight for planetary science more broadly. It tells us that on small, cold, geologically quiet worlds, the consequences of early events are permanent. A single impact, occurring in the first few 100 million years of a world's existence, can establish a chemical asymmetry that shapes geological evolution for the remaining 4 billion years. The Moon did not gradually arrive at its two-phase configuration through slow, incremental processes. It was configured by a catastrophe, suddenly, violently, and irreversibly, and the evidence of that configuration is written in every rock, every crater, every gravitational anomaly, and every chemical gradient that instruments can measure. The far side also forces us to confront an uncomfortable truth about the radiation environment of the Earth-Moon system. Data from China's Chang'e 4 lander, published in Science Advances in March of 2026, revealed a cavity of reduced galactic cosmic ray radiation near the Moon, associated with the tail of Earth's magnetosphere. Galactic cosmic rays, high-energy protons and heavier nuclei accelerated by supernovae and other violent astrophysical events, are among the most serious health hazards facing astronauts beyond low Earth orbit. They penetrate spacecraft hulls, spacesuits, and human tissue. They break DNA strands. They increase the risk of cancer, cardiovascular disease, and neurological damage. They cannot be fully shielded against using any practical thickness of material. The prevailing assumption was that cosmic ray radiation would be approximately uniform across the Earth-Moon distance. The Moon is far from Earth. The magnetosphere is strong near Earth, but attenuates rapidly with distance. Why would radiation levels vary at lunar distance? The expectation was simple. Once you leave the protection of the Van Allen belts, the radiation belts that encircle Earth at distances of roughly 600 to 36,000 miles. You are in open space, exposed to the full flux of galactic cosmic rays. It should not matter whether you are behind the moon, or in front of it, above the near side or below the far side. The cosmic ray environment should be the same everywhere at that distance from Earth. But the Chang'e 4 data showed that they do vary. When the moon passes through the tail of Earth's magnetosphere, the elongated wake of magnetic influence that streams away from Earth in the anti-solar direction, the galactic cosmic ray flux drops measurably. The cavity is not large and it is not permanent. It appears in specific orbital positions and at specific local times on the lunar surface. But it is real, and it represents an unexpected extension of Earth's protective influence to distances of 239,000 miles and beyond. The implications of this discovery are both scientific and practical. Scientifically, it tells us something new about the structure of Earth's magnetosphere at distances far beyond the magnetopause, the nominal boundary where the solar wind pressure balances the magnetic field pressure. The magnetotail extends millions of miles into space, streaming away from Earth like a comet's tail, and its structure at lunar distance is not well characterized. The Chang'e 4 data provides ground truth, or rather moon truth, for magnetospheric models that have been calibrated primarily using satellites in near-Earth orbits. The data shows that the magnetotail retains enough coherent magnetic field structure at lunar distance to partially deflect incoming galactic cosmic rays, reducing the flux by a measurable amount. This was not predicted by most models. Practically, the discovery has implications for the design and scheduling of future lunar surface operations. Galactic cosmic rays are the most dangerous form of radiation for astronauts because they consist of heavy nuclei, fully ionized atoms of elements like iron, silicon, and oxygen, traveling at significant fractions of the speed of light. When these nuclei strike biological tissue, they leave trails of ionization damage that are far more destructive than the damage caused by lighter radiation like protons or gamma rays. A single galactic cosmic ray nucleus can destroy dozens of cells along its path through tissue. Over the course of a long lunar surface mission, the cumulative damage from galactic cosmic rays increases the crew's risk of cancer, cardiovascular disease, cataracts, and cognitive impairment. There is no practical shielding solution. Unlike solar particle events, which can be blocked by a few inches of material, galactic cosmic rays have so much energy that shielding actually makes the problem worse. The incoming nucleus strikes the shielding material and produces a shower of secondary particles that can be more damaging than the original nucleus. Any natural reduction in the galactic cosmic ray flux, even a modest one, is therefore significant. If future mission planners can schedule surface operations to coincide with periods when the moon is within Earth's magnetotail, which occurs for roughly 6 days each month, they could reduce the crew's cumulative cosmic ray exposure without any additional mass or engineering. The reduction might be modest, perhaps 10 to 20%, based on the preliminary Chang'e 4 data, but over the course of a months-long surface mission, even a 10% reduction in cosmic ray exposure translates to a meaningful decrease in long-term health risk. The Artemis 2 crew contributed to the radiation picture through the AVATR investigation, a suite of experiments studying how human tissue responds to microgravity and the deep space radiation environment. Blood and tissue samples from the crew, collected before, during, and after the mission, will provide the first direct measurements of how cosmic radiation affects human biology during a lunar flyby. The crew spent 10 days beyond the protection of Earth's magnetosphere, exposed to radiation levels far higher than those experienced on the International Space Station. Their biological data, correlated with the radiation measurements from onboard instruments, will help NASA assess the health risks of extended lunar operations and develop strategies for protecting future crews. The convergence of these findings, the impact history, the internal asymmetry, the radiation environment, the volcanic persistence of the far side, paints a picture of the moon that is richer, stranger, and more deeply connected to Earth than anyone imagined at the start of the space age. The Moon is not an inert companion. It is the other half of a dynamic system, linked to Earth by gravity, tidal forces, reflected light, magnetic influence, and a shared history of violent formation. The far side is where the most important evidence of this relationship lies. Evidence that has been accumulating, undisturbed, for billions of years. We are accustomed to thinking of the Moon as a destination, a place to visit, a target for rockets, a stepping stone to Mars. But the Moon is also a mirror. Not a mirror in the optical sense, though it does reflect sunlight toward us every night. It is a mirror in the geological sense. It reflects the history of the Earth-Moon system back to us, in a form that Earth itself can no longer provide. Every question we ask about Earth's early environment — what was the bombardment rate? When did it decline? How intense were the largest impacts? What was the radiation environment? When did conditions become stable enough for life? Can be addressed, at least in part, by studying the Moon's far side. The far side is not just lunar history, it is Earth history, preserved on an adjacent world because our own world could not keep it. The Artemis 2 crew spent 7 hours flying over this evidence. They photographed it, described it, and experienced it directly. The flashes, the craters, the eclipse, the Earthset, the silence. They were the first human witnesses to the full far side in more than 50 years, and their testimony, thousands of photographs, hours of audio recordings, pages of transcribed observations, is now being archived on NASA's planetary data system, available to the global scientific community for analysis that will take years to complete. The value of this testimony extends beyond the data it contains. It establishes a baseline, a record of what trained human observers saw when they looked at the far side under specific lighting conditions, from a specific trajectory, at a specific moment in time. Future missions will see the far side under different conditions. By comparing observations across missions, scientists can detect changes, new craters, shifts in surface reflectivity, variations in dust distribution that accumulate over years and decades. The Artemis 2 observations are not just a snapshot, they are the first frame of a time-lapse that will eventually reveal the far side's ongoing evolution. The far side is no longer hidden, but it is very far from understood. Each new mission, each new sample, each new observation reveals layers of complexity that demand further investigation. The Moon is not a simple world. It is a 4.5 billion-year-old puzzle, and we have only just begun to assemble the pieces. So what does all of this mean? Not just for scientists, not just for NASA, not just for the 4 astronauts who flew 252,756 miles from home, and then came back to tell us about it. What does it mean for us? For anyone who has ever looked up at the Moon and seen a familiar face, a comforting light, a silver disk that appears every night and disappears every morning, as reliable as the sunrise, as ordinary as breathing. It means we have been looking at half a story. Less than half, actually. The face the Moon shows us, the near side, with its dark splotches and bright rays, the face that has inspired poets and navigators and lovers for as long as human beings have possessed language, is the altered face, the remodeled face. The face that was reshaped by billions of years of volcanic eruptions, flows of basaltic lava filling enormous basins, burying the original surface beneath layers of dark rock. What we see when we look up at the Moon is the geological equivalent of a renovated house. The original structure is still there, buried underneath, but the surface has been redone. New floors, new walls, new paint. The character of the original construction is hidden. The far side is the unrenovated wing, the part of the house that nobody touched, the part where the original woodwork is still exposed, where the original plaster is still on the walls, where the foundation stones laid down by the first builders are still visible. It is older, rougher, less polished, less photogenic, but it is authentic. It is the real thing. It is the Moon as it was before volcanism transformed the near side into the smooth, dark-patched face we know. And that original face has something to tell us, something important, something that goes beyond lunar geology, beyond planetary science, beyond the academic boundaries of any single discipline. It tells us about the birth of the Earth-Moon system. The far side preserves the chemical and structural signatures of the giant impact that formed the Moon. The catastrophic collision between proto-Earth and a Mars-sized impactor called Theia, roughly 4.5 billion years ago. The thick far-side crust, the depleted far-side mantle, the absence of creep, the ancient highland surfaces. All of these features carry information about the conditions that existed in the first 100 million years of the Moon's existence, when the lunar magma ocean was crystallizing, when the crust was solidifying, when the fundamental architecture of the Moon was being established. We cannot access this information on Earth. Our planet's geological engine has destroyed the evidence. The Moon's far side has preserved it. It tells us about the bombardment that shaped the early inner solar system. The far-side highlands are the most complete record of the late heavy bombardment that exists anywhere we can reach. Every crater is a timestamp. Every degraded rim, every ghost crater, every overlap where a newer impact has partially obliterated an older one. All of these relationships encode a chronology of violence that extends back to the first few 100 million years of the solar system. This chronology matters because it constrains when Earth's surface became habitable. If the bombardment was intense enough and lasted long enough, then life could not have emerged until it subsided. If the bombardment tapered off gradually, then life may have arisen earlier, perhaps gaining a foothold in deep subsurface environments, while the surface was still being periodically sterilized by large impacts. The timing of life's origin on Earth is one of the most important questions in all of science. The far side of the Moon holds critical evidence for answering it. It tells us about the internal dynamics of a differentiated world. The Moon is small, only about 1/4 the diameter of Earth, and about 1/80th of its mass. But it is a differentiated body. It has a core, a mantle, and a crust. It had a magnetic field. It had active volcanism. It had internal convection and thermal evolution and chemical processing. The far side reveals what happens when a small, differentiated world loses its internal heat. How volcanism shuts down, how the mantle freezes, how the magnetic dynamo fails. These processes are universal. They have occurred or are occurring on every rocky body in the solar system. Studying them on the Moon, where the geological record is exposed and accessible, teaches us about Mars, Mercury, the asteroids, and every rocky exoplanet orbiting every star in the galaxy. The Moon is a laboratory for planetary evolution, and the far side is where the most revealing experiments have been preserved. It tells us about the radiation environment beyond Earth's protection. The Chang'e 4 discovery of a cosmic ray cavity near the Moon, correlated with Earth's magnetotail, has practical implications that extend far beyond academic interest. If certain orbital positions or lunar surface locations experience measurably reduced radiation levels at certain times, the information could influence the design and siting of future lunar habitats. Radiation is the single greatest obstacle to long-duration human presence beyond low Earth orbit. Any natural phenomenon that mitigates radiation exposure, even partially, even intermittently, could meaningfully affect mission architecture and crew safety. The far side, specifically, the far side at those times, when the Moon passes through Earth's magnetotail, may offer radiation conditions that are slightly less hostile than the near side or than other orbital positions. This possibility demands further investigation, and the Chang'e 4 results provide the foundation for that investigation. We are, in a real sense, still tethered to Earth, even at lunar distance. The magnetotail is an invisible umbilical cord, a tenuous extension of the magnetic cocoon that has sheltered life on Earth for billions of years. Its influence reaches farther than anyone expected, and the Moon, orbiting through this extended shelter once a month, provides the natural laboratory where we can study its properties and test its limits. And it tells us something about ourselves, something that has nothing to do with geology or physics or chemistry. It tells us about the limits of observation and the dangers of assuming that what we can see is all there is. For all of human history until 1959, no one had ever seen the far side of the Moon. Not once. Not in any culture, in any civilization, in any era. The Moon presented one face to Earth, and we saw it, and we mapped it, and we named its features, and we assumed, without ever articulating the assumption, because it was so fundamental as to be invisible, that what we saw was representative, that the Moon was the Moon, that the face it showed us was a fair sample of the whole. It was not. The two hemispheres are profoundly, structurally, chemically, geologically different. They have different crustal thicknesses, different volcanic histories, different surface compositions, different crater densities, different internal heat budgets, different mantle chemistries. They are, in a real and measurable sense, two different worlds joined at the equator. And we had no way of knowing this until we sent a spacecraft around to look at the other side. This is a parable, whether we want it to be or not. A parable about the danger of generalizing from visible evidence. A parable about the humility that should accompany any claim of knowledge. A parable about the universe's persistent tendency to be more complicated, more asymmetric, more surprising than our theories predict. We observed one face for millennia and built an entire understanding of the moon around what we saw. That understanding was incomplete. Not wrong, exactly. The near-side observations were accurate as far as they went, but fatally incomplete, because the half we could not see turned out to be fundamentally different from the half we could. The moon was supposed to be simple. A small, airless, geologically dead world with a straightforward formation history and a predictable internal structure. Instead, it is asymmetric, complex, zoned, active, in subtle ways, and full of features that challenge our most fundamental models of planetary formation and evolution. If the moon, our nearest neighbour, the most studied extraterrestrial body in the solar system, a world we have visited 6 times with human crews, can still surprise us this thoroughly, what should we expect from Mars? From Europa? From Enceladus? From the rocky planets orbiting other stars? The answer is more surprises, more complexity, more asymmetry, more reasons to look at the side we haven't seen yet. This lesson extends far beyond the moon. Mars, our next target for human exploration, is also asymmetric. Its northern hemisphere is dominated by smooth, low-lying plains. Its southern hemisphere is dominated by ancient, heavily cratered highlands, a dichotomy strikingly reminiscent of the moon's own two faces. The Martian dichotomy is even more dramatic than the lunar one. The difference in elevation between the northern lowlands and the southern highlands averages about 3 miles, and the boundary between them is one of the most prominent geological features on the planet. The cause of Mars's hemispheric asymmetry is debated, with proposed explanations ranging from a single, giant impact in the northern hemisphere to mantle convection patterns that eroded the crust from below. The parallels with the lunar asymmetry are obvious and instructive. If we can understand why the moon has 2 faces, we may be closer to understanding why Mars does as well, and by extension, whether hemispheric asymmetries are a common feature of rocky planets throughout the galaxy. This matters because the habitability of a planet depends on its geological evolution. The volcanic eruptions that filled the near-side Maria released gases, carbon dioxide, sulfur dioxide, water vapor, that would have temporarily altered the moon's tenuous atmosphere with each eruption, on a body with enough mass to retain an atmosphere, like Mars, or like the rocky exoplanets being discovered by the thousands around other stars. Volcanic activity is a primary mechanism for building and maintaining an atmosphere, cycling volatiles between the interior and the surface, and creating the chemical conditions for liquid water. If hemispheric asymmetries control the distribution of volcanism on rocky worlds, then they may also control the distribution of habitability. One hemisphere might be geologically active, atmospherically productive, potentially life-supporting. The other might be dead. The moon, being too small and too airless for these processes to produce habitability, serves as a controlled experiment, a case study in how asymmetry shapes geological destiny on a world where the results are unambiguous and the evidence is preserved. The Artemis II crew understood this. You can hear it in their voices on the archived recordings. When Reed Wiseman described the far side as humbling, he was not performing humility for the cameras. He was reporting an experience. When Victor Glover described the Terminator as magical, when he used the phrase islands of light and valleys, like black holes, he was reaching for language adequate to an experience that exceeded his expectations. These are test pilots and engineers and military officers, people trained to be precise, calibrated, unsentimental, and they came back from the far side sounding like poets, because the far side demands poetry, because the scale and the age and the silence and the strangeness of what they saw cannot be fully captured by the technical language of orbital mechanics or geological survey. 7,000 photographs, 6 impact flashes, 54 minutes of solar eclipse, 40 minutes of radio silence behind the moon, completely cut off from Earth, seeing nothing but ancient craters and black sky, and eventually, the sun's corona rising like a crown of light behind the lunar limb. These are not just data points, they are experiences. They are moments of human consciousness in contact with the deep history of the solar system. And they happened because 4 people climbed into a spacecraft, pointed it at the moon, and went to look at the side they hadn't seen. The Artemis 2 mission ended on April 10, 2026, when the Orion spacecraft, call sign Integrity, splashed down under 3 enormous orange and white parachutes into the Pacific Ocean off the coast of San Diego. The capsule hit the water after 10 days in space, having traveled 695,081 miles at speeds up to nearly 25,000 miles per hour. Recovery teams from the USS San Jacinto reached the capsule within minutes. The crew was healthy, the spacecraft was intact. The mission was, by every technical metric, a success. But success is a thin word for what happened. What happened was that human beings went farther from Earth than any human being has ever gone. What happened was that they rounded the moon, a body that most people treat as a decoration in the night sky, and discovered that its hidden hemisphere is a geological archive of staggering complexity and antiquity. What happened was that they saw meteoroids strike the lunar surface, watched the sun disappear behind the moon for nearly an hour, experienced a silence so deep that the absence of radio signals was itself a kind of message, a reminder that the moon is a real place, a physical body interposed between them and everything they had ever known, blocking not just light but communication, contact, connection. What happened was that they came home changed, not in any dramatic, cinematic way, not with alien artifacts or mysterious signals or evidence of extraterrestrial life. They came home with photographs and observations and blood samples and a story about a world that is simultaneously the most familiar and the most alien object in our sky, a world we see every night and have never truly seen, a world that is telling us something about ourselves, about our origins, our environment, our vulnerability, our astonishing good fortune in living on a planet where the conditions for life happen to converge. If only we are willing to listen. The far side of the moon is not terrifying in the way that movies and television shows use that word. There are no monsters, no ancient alien ruins, no malevolent forces lurking in the permanent darkness of shadowed craters. The far side is terrifying in a deeper, older sense of the word, the sense that relates to awe, to the experience of confronting something so vast and so ancient and so indifferent to human concerns that it recalibrates your sense of scale. The far side is 4.5 billion years old. It has been sitting there, accumulating craters, recording impacts, preserving its original chemistry, while Earth generated and destroyed entire supercontinents, while oceans formed and evaporated and reformed, while life arose from chemistry and evolved from single cells to conscious minds capable of building spacecraft and flying them to the moon. The far side does not care about us. It does not know we exist. It was there before us, and it will be there after us, and nothing we do will alter its fundamental nature. And that is what is terrifying. Not the darkness, not the silence, not the craters, or the buried mass anomalies, or the radiation. What is terrifying is the scale of time. What is terrifying is the realization that the moon, our moon, the one we hang mobiles of in children's bedrooms, the one we use as a metaphor for impossible promises, the one we see so often that we forget to see it at all, is older than anything we can meaningfully comprehend. The rocks beneath the Artemis 2 flight path were formed before there were oceans on Earth, before there was oxygen in the atmosphere, before there was life, before the continents existed, before the magnetic field stabilized, before the late heavy bombardment ended, before anything on Earth that we would recognize as Earth. The moon remembers what Earth has forgotten. That is the terrifying part. Our planet has Alzheimer's. Its geological memory is fragmented, rewritten, destroyed by plate tectonics and erosion and volcanism and metamorphism. The moon has perfect recall. Every impact, every eruption, every ray of cosmic radiation, every grain of solar wind, recorded, preserved, waiting to be read. And the far side, with its ancient highlands and its untouched surfaces and its absence of the volcanic resurfacing that wiped the near side's early record, is where the most important memories are stored. We sent 4 people to look at those memories. They flew over them at thousands of miles per hour in a spacecraft named for a concept, integrity, that implies wholeness, completeness, the state of being undivided. They saw what they saw. They photographed what they photographed. They came home and they told us. Now, the question is what we do with what they told us. The Artemis program continues. Artemis 3 is planned to land humans at the lunar South Pole, near the rim of the South Pole Aitken Basin, within reach of the permanently shadowed craters where water ice may persist. Future missions will establish surface infrastructure, habitats, power systems, communication relays, scientific instruments. The goal, stated explicitly by NASA, is a sustained human presence on and around the moon, not a visit, a presence. People living and working on the lunar surface for weeks and months at a time, conducting science, testing technologies, preparing for the longer and more dangerous journey to Mars. If that vision is realized, and there are significant political, budgetary, and technical obstacles between here and there, then the far side will eventually receive human visitors on the ground, not flying over it at altitude as the Artemis 2 crew did, but standing on it, walking on it, picking up rocks and examining them, drilling into the regolith and extracting cores, setting up seismometers and magnetometers and radiation monitors, building the infrastructure of permanent scientific investigation on the most pristine geological surface in the accessible solar system. When that happens, if that happens, we will begin to read the moon's far side record in detail, not from orbit, not from photographs taken through spacecraft windows at 400 millimeters of focal length, not from 2 kilograms of robotically collected soil, but from systematic, sustained hands-on geological exploration conducted by trained human scientists with the tools and the time and the institutional support to do the job properly. And what they find will change everything. It changed everything when we went to the near side with Apollo. The samples those missions brought back, 382 kilograms of rock and soil from 6 landing sites, transformed our understanding of the moon, the Earth-Moon system, and planetary science as a whole. The far side, with its ancient surfaces and its preserved record of the early solar system, will yield discoveries at least as significant, probably more so, because the far side has been waiting longer, because it has more to tell, because it has been keeping records that the near side lost billions of years ago, and those records are exactly the ones we most desperately need. The Artemis 2 crew got a preview. 7 hours of flyby, 7,000 photographs, 6 impact flashes, 1 solar eclipse lasting 54 minutes, 1 Earthset, 1 Earthrise, 1 period of complete radio silence lasting 40 minutes, during which 4 human beings were more alone than any human beings have ever been. Farther from home, cut off from contact, surrounded by ancient terrain that predates life on Earth by 1 billion years. They saw the far side, they saw what it holds. They came home and told us it was humbling and magical and terrifying and beautiful, and that the greens and browns of the regolith surprised them, and that the Terminator was unlike anything they had been trained to expect, and that the impact flashes were real. 6 brief sparks of creation and destruction, visible to the naked eye, on a surface that had been recording those sparks for 4.5 billion years. The moon's far side is terrifying because it is real. Not because of what might be hiding there, but because of what is plainly, visibly, measurably, undeniably there. A record of our origins, written in stone, older than memory, older than life, older than the Earth we live on, and more complete than anything we have access to anywhere else in the known universe. We looked, we saw. We have only just begun to understand. The moon will be there tomorrow night. It will rise as it has always risen, pale, silent, familiar. You will see the same face that every human being who has ever lived has seen. The Maria Tranquillitatis, the Mare Imbrium, the bright ray system of Tycho, spreading outward like the spokes of a wheel from a crater formed 108 million years ago, when dinosaurs were still walking the Earth. you will see the face you know, the decorated face, the volcanically remodeled face, the face that has inspired 10,000 years of mythology and poetry and science. Behind it, invisible, untouched by your gaze, the far side will be turning in silence. Its craters will be accumulating microscopic layers of space dust, just as they have for 4 billion years. Its regolith will be shifting imperceptibly under the thermal stresses of the 2-week-long lunar day and the 2-week-long lunar night. And somewhere on that ancient surface, at some unpredictable moment, a meteoroid will arrive from deep space and strike the ground at 40,000 miles per hour, creating a flash that no one will see, adding one more crater to a record that stretches back to the beginning of the solar system. The far side remembers. It has always remembered. It will go on remembering long after we are gone, long after our civilization has risen and fallen and been forgotten, long after Earth itself has been rendered uninhabitable by the slow brightening of the sun. The far side is patient. It is indifferent. It is the most complete record of our solar system's history that exists anywhere within our reach. And for 7 hours on April 6, 2026, 4 human beings flew over it, looked down, and began to read.